First, before I get started, I just want to tell you that there are excellent references for C++ online. There's a great tutorial here at cplus.com/doc/tutorial. So if you want to, before the class really gets going, if you want to go practice some C++, that's a great way to do it, to follow along with that tutorial. Also, learncpp.com has a great tutorial. They may not be teaching C++ at the same level that we're teaching it in the course. They may go from a very, very ground up approach, but it's not bad to have that, that background material. And whenever you Google something about C++, which will be quite often in this course, because I still do it, so I assume you're going to do it. Like if you say like how to read a file in C, or C++, sorry, or vector in C++, or how to add to a map in C++, this is pretty much the site that you're going to get back. So there's going to be some Stack Overflow, but this is the go-to reference for all the standard template libraries and functions for C++. You don't really need to bookmark that, because every time you Google, you're going to get this, this reference come up. And I apologize if I'm drinking often, or if I'm coughing or something like that. This is my second day of teaching for the year, and if you've never spoken for 3 hours straight, it takes a bit of a getting used to. So it's still the second term of the year, second lecture of the year. So I apologize if I'm taking a break every now and then. So, speaking of breaks, what is C++? I'm sure you've all heard of it, probably through horror stories, but I promise you it will not be as bad as you've heard. So C++ is a programming language that focuses on runtime speed, so it wants to be able to be as fast as possible, and also on functionality, okay? So you can do pretty much anything in C++. C++ is a compiled language. So there are languages out there that are not compiled. So for example, Python is an interpreted language, meaning that there's an interpreter that runs in the background that looks at your code line by line and will only throw runtime errors, okay? C++ is a compiled language like Java, right? And so you're going to type a command that will compile your code, and you may get compiler errors. No, sorry, you will get compiler errors. So just know that it's a compiled language. Some people say that C++ is a low-level language. I don't think that's true, because there's a lot going on under the hood in the compiler. So low-level to me means like full control. And C++, you just type a regular program. There's a lot of stuff that the compiler is doing that it's not telling you. So I would say that C++ is a mid to low level programming language if you are obsessed with these sort of hierarchies of programming language. So what do I mean by a mid-level programming language? Well, assembly would be a low-level programming language, right? You're speaking almost the same language that the computer understands, and a high-level language would be something like Python, right? Where you're not saying as many details when you program. The programming language is taking care of a lot more of it for you. But the trade-off with levels of programming languages is that in a high-level language, you're going to have to probably type less code. You're going to get, code that looks a little bit more understandable to a new programmer. But the trade-off there is that it won't be as fast, right? So the lower level, ideally, the faster your code can be. Now, that doesn't mean that everything you type in C++ is going to be fast. In fact, when you start out with C++, your code may actually be slower than the same code in Python. And the reason for that is you need to know how to manage things in C++ before it starts to get very fast. So just keep that in mind, that C++ is not automatically very fast. So I went online, I found some memes about C++ because I'm a big memer. So like, what are you studying C++? Oh, you poor child. Like, don't worry, it's not going to be as bad as you've heard, all right? I know you've seen all the memes, you've heard all the horror stories. We're going to get through this course. Nobody has ever complained in the history of this course about C++ being the bottleneck, okay? And that doesn't mean that everything else is super hard either. It's just that we teach enough C++ to get you by. You'll be fine. C++ is not something that you can just learn overnight, okay? So it's a lifelong process of learning C++. And probably the most confident you will ever feel about your ability in C++ is right now. Because the more you learn about C++, the more you know that you don't know about C++. And so there's a real Dunning-Kruger effect with C++. And just keep in mind that like we're going to be learning, but it's not going to be an instantaneous process. So if you have trouble at first, you are not the only one. And of course, I love this one. So, you know, first year of C++, you're going to be hitting this rake. It's going to smack you in the face. 10th year of C++, you're basically doing a lot more fancy stuff before you hit yourself in the face, right? So just keep in mind, just a little bit of humor before we jump into the snake pit of C++. All right. So what are some advantages of C++? There's got to be some advantages or it wouldn't be around, right? All right. So the first advantage, it's very widely used and supported. It's very prevalent in the games industry, especially. So if you're going into the games industry, you probably want to know some C++. There are many libraries available for C++. Basically anything that you can do on a computer, you can find a library out there that does it in C++. The resulting code, and now with a caveat, that the resulting code, if you know what you're doing, can be very fast. So maybe I should change that line, but like properly programmed C++ will be quite fast. The syntax is very similar to Java and other programming languages that you may be familiar with. Like, no, it's not the same thing as Java, but you will see that if you've programmed in Java, and just please type out in the chat if you have programmed in Java, or even JavaScript, the syntax is quite similar. Now, I mean, there are things that are different, obviously. Like once you start getting into templates and, you know, instead of using like : for namespaces, there's differences. But overall, if you showed someone like who didn't know programming, a C++ program and a Java program, they would almost look identical, right? C++ programmers get hired, right? Okay, so a lot of people have used Java. That's excellent. If you can program in C++, you've kind of, you know, that's sort of the boot camp of programming languages, right? So a lot of companies out there, if you can program in C++, you can certainly program in Python, right? So C++ programmers, you're gonna get hired. The code is highly customizable. So you can operator overload, you can define things. That ends up being one of the disadvantages as well. But like, it's your playground. C++ is yours to shoot yourself in the foot with, right? And C++ will be around for a long time. It's not going anywhere. You know, there's all these memes out there about like, you know, every year there's a new C++ killer, like Rust or I can't remember Google's new language that they think they're going to end up supporting. That'll be like the what is it? The Google wave of programming languages. There's lots of languages out there that are supposed to be the C++ killer, right? There's lots of MMOs out there that are supposed to be the WoW killer. It's not going anywhere. C++ is here to stay. That being said, there are some disadvantages of C++. It's very easy to write unsafe code and to crash in C++. That is probably the biggest disadvantage, or at least it used to be the biggest disadvantage, right? There are modern C++, it is very easy to write safe code. However, the possibility exists that you'll still write unsafe code. Okay, so you must manage your own memory. So it is not a garbage collected language. This is a turnoff to many new programmers because managing memory is not something you really want to learn about as your first programming language. Maybe you do. I don't know. There's different schools of thought there. But what we'll show in this course is through a technique called RAII and through the factory that we'll make for the entity manager, you will never have to worry about memory once we get our engine up and running, okay? So even though you have to manage your own memory, there are good software engineering principles in C++ so that it almost looks like you don't have to manage your own memory. The syntax of C++ can be a little bit confusing, okay? We will handhold you through that. Don't worry about that. I would say that maybe the biggest disadvantage of a seasoned C++ programmer is that it can be hard to read other people's code sometimes. And the reason for that is because of one of the advantages of C++ is that there's custom definitions, there's operator overloading, there's all sorts of ways that you can customize the things that your code does, to the point that if I'm just looking at one screen of code, the same code in my library may actually be doing a different thing than in your library. So it can actually be a little bit hard to read other people's code if they've gone down that rabbit hole of all these custom definitions and stuff. All right. And of course, probably your biggest worry this term will be interpreting compiler and linker errors in C++. Because, there's that meme that, your experience of C++, the time spent coding, like typing characters versus dealing with compiler and linker errors is probably going to be similar to this graph for the first little while, right? And also, C++ doesn't know what to do with a 0, right? Is it an int? Is it a bool? Is it a pointer? Is it an array? Is it a null? So there's all these memes about C++ and how it treats some data structures. And this is true if you do really, really old school, low level C++ programming. But don't worry, we probably won't run into this kind of stuff in our course. Before we talk about C++, I'm going to talk about a little bit of the history. I'm not going to dive too far into the weeds, but we need to talk about the C programming language. C was created by Dennis Ritchie at Bell Labs in the 1970s. Please say something out there in the chat if you've used C++. Ooh, I have a little poll thing out here. All right, so let me add an option. Programming languages you have used. I didn't realize there was a poll here. This is great. So let's go with C, C++. I'm not going to list every programming language. Java, Python. Okay, I can only have 4 options, so let's ask my community. All right, so I've got a poll out there. I think you can click that in the chat. Maybe it's at the top of the chat. That's my first ever poll on YouTube. Excuse me. So look for that and answer that poll for me. So the C programming language was created in the 1970s. It's available on nearly every platform. I assure you that if you have a piece of hardware, C runs on that piece of hardware. It probably runs on your oven or your stove, right? C is out there for everything. It's crazy. It is a procedural low to mid-level language. Oh, you can only select one option in the poll? Oh, sorry about that. Okay, well, I know that for the future. So polls are multiple choice, not multiple select. So thank you for that. I guess that poll is useless, but a lot of people, half the class said they've used C, so that's great. All right, so C is a procedural mid to low level language. There is no built-in object-oriented programming in C. So C is very popular for system software. Very famously, Linux is written in C for writing drivers, embedded stuff, operating systems, etc. Okay, so C is the programming language you probably want to use when you want things as fast as possible, as low level as possible, and you want your executable size to be as small as possible. Okay, and C, of course, greatly influenced the development of C++. So what is C++? Well, the C++ programming language was created by Bjorn at Bell Labs, and originally he called it C with classes. Okay, so C++ was called C with classes in 1983. And it is, again, a procedural language, and you can say that it is a superset of C. Now, I know people who are very, very good C++ programmers, far better C++ programmers than me, that take issue with the calling of C++ a superset of C. And what do I mean by a superset of C? It means that basically anything you can do in C can also be done in C++. So if you write almost any C program, a C++ compiler can handle it. However, there are exceptions to this. What those exceptions are barely ever come up in practice, okay? So don't come yelling to me that, oh, I found an example. For all practical purposes, you can write C inside a C++ program. I don't think anyone could argue with that. It's just me saying that this is how C relates to C++. Is that C++ contains C with, quotation marks around contains, and then there's more functionality on top of that. A lot more functionality, almost to the point where when you wrote older C++, you would see a lot of C-like syntax, but in modern C++, you almost never want to see C-like syntax. Unless, I say these things, there's always caveats. Of course, some people use C++ to just say, use C with templates, right? So some people want C to have templates, so they use C++ for that. That's fine, that's a very niche example, but in this we are going to be making full use of C++ with the standard template library and modern functionality. Okay. C++ supports object-oriented programming, so we have classes, we have inheritance, and we have generics, meaning that we can have a vector of ints, right? So we have templates in C++. We'll get all into that in the next lecture. It maintains the efficiency of C, of course, maybe not 100% the efficiency of C, but within a few percent of C. And it's very, very popular in video game development, and C++ helped influence the development of other languages such as C# and Java. All right. Now we have to talk about C++ versions, because just like Python has versions, Java has versions, C++ has versions. And C++ versions actually do matter. So, C++ first appeared, it was created in 83, the official name was in 85. The first final standardized version, was C++ 98. And that is, C++ 98 is, I think, what ruined a lot of people for C++. Things were very verbose. They were kind of hard to do. Iterators were very verbose. Lots of things in C++ 98 were very annoying. C++ 11 came along with many, many new features and quality of life improvements. And I think C++ 11 is where I started to really love C++, and a lot of people, because it really did, it brought modern C++ into the era of ease of programming with things like Java and Python, right? Then there's C++ 14, 17, 20, I think 2022 is either out or in production. There's lots of different versions. It's basically the year that it was released, and they all introduce new features, some of which you may run into, some of which you may never run into. I think I have used a total of 2 features from C++ 20 that weren't in C++ 17, and I write a lot of C++ code. We will be using at least C++ 17 in this course, okay? So there's a lot of nice new functionality over C++ 98, and the compiler flag we're using is, so in order to tell your compiler to use the new functionality, because for some reason it defaults to the old functionality, is you have to say -standard equals C++ 17. Okay, so when you run your compiler, you have to put that in the command. Now, Visual Studio will do that for you. We'll set that in the project files, but if you're doing this command line, you just have to make sure that you do that. So we've got this sort of it kind of seems like this from the outside, where someone took C and made C++, and then, you sort of just keep adding on. And this is actually a legitimate issue. I sort of display this as a meme, but as more and more functionality gets added to C++, as someone who loves C++, you almost wish that they could tear it down and just make a new one and not have the old stuff in it. And so it's, some stuff gets deprecated, some stuff gets added. It's a little bit annoying. You won't have to worry about any of that in this course, of course. We're just going to use the C++ that I show you. But it is kind of an issue. And when you're evangelizing the use of a language for a course, you should also say the bad things about a course, right? Or sorry, the bad things about a language. And this is, I would say it is a bad thing about C++, is over time, the amount of stuff that gets added to it gets a little bit confusing and makes it a little bit ugly and stuff like that. But again, you won't have to worry about all that in this course. Okay. What are some properties of C++? C++ is statically typed, okay? So variables are defined and typed before they are used, right? So if you've used C or you've used Java, it's the same thing. But if you've used Python, Python is not a, I'll show you that in a second. So if we want to have a year, we have to have it declared as whatever data type we want. So for example, years are integers, right? So int year equals 2018, 2022, whatever. You can tell when I made these slides, right? Java and C are also statically typed. Variable types are defined at compile time. Okay, so later on, if I want to have year store a floating point, I can't do that. It's defined at compile time. Okay, Python and JavaScript are dynamically typed. So you would just say num equals 10, right? So the variable types are defined at runtime. If you want to overwrite that variable that was an integer with a string, you can totally do that, right? So just realize that like C++ is statically typed and Python and some other languages are dynamically typed. So let's look at your first C++ program. And of course, we are a computer science course. We've got to use the hello world. So this is your first C++ program. It prints hello world to the screen. I am going to go through this line by line for the people who are new to C++, and maybe for even if you've typed this in before, maybe you don't exactly understand what's going on, right? And if you've never seen C++ before, if you're used to other programming languages, this may be what you're looking at, right? Okay, console.log hello. Yeah, that makes sense. Here we've got some JavaScript. System.out.print hello. Okay, it's printing out to the system. Hello. Yeah, okay, I can see that. Standard : C out left hello left standard. Yeah. Like, what is all this stuff, right? It looks like a foreign language. Well, it might be a foreign language. It is a language, right? But what does all this stuff mean? Why is it like that? We're going to explore why it's like that and why, to me, it's actually better like that. Okay? So let's go through that hello world program line by line. And you might, at this point, you're saying, oh my God, he's teaching like hello world and we're going to be making a full game engine? Yes. It's remarkable how quickly you can learn enough C++ to program games. So don't worry, we're not going too slow. It will ramp up in a couple of lectures. So include IO stream. That's the very first thing that happens in your program. What the hell is that? So the first line is called a preprocessor directive, okay? So we're going to talk about the preprocessor later, but essentially this hashtag include is used to include a C++ library, right? So you've probably seen this in Java before. Does Java use include? Yeah, I think Java's include or import. Just it's been 10 years since I've written a Java program. So in Python you've got import, in C and C++ you've got include. So you've got include and the name of that library. This particular library, IOStream, is used for input and output streams, okay? So what is a stream? We will be talking about what a stream is, but an IOStream will allow us to use the standard cout to print to the console. So standard cout is the object, and we'll talk about this in a little bit, that lets us print to the console, okay? So let's move on, and I'll give more details on all this later. I'm just going through line by line. Next, we have int main int argc comma char star argv bracket bracket. Okay, so if you're familiar with Java, right, that's your public static void main string args. That's the exact same thing. That's what this is. Each C++ program must have a main function which is run when the program starts. So you've got to have a main, all right? That's the same thing with Java. Okay, with Java console apps at least. The contents of this function are enclosed in brackets, just like in Java. The main function has an int return type, okay? So this int here, in Java, for example, it's public static void main. Void does not have a return type in Java. It does have a return type in C. We'll talk about that in a bit. The main function has int return type. argc is the number of program arguments, and argv is the array of strings that you pass into it. So string args in Java strings are objects, and Java arrays are objects. So the Java array object knows its own length, okay? Now this is, we'll get into pointers and all kind of stuff later, but the whole reason for this int argc is because a raw C++ array pointer does not know its own length. So we've got to pass in the array itself as well as the length of that array. And this just processes command line arguments. So if you type your program and then a bunch of arguments after it, that's what this is processing, okay? We're actually not going to use this whatsoever in the course. It's just there, okay? And I believe you could actually just type int main without this. It might throw you an error in one compiler, it might not in another compiler, but it is what it is. All right. Standard cout, this thing, what the hell is that? Hello world /n. Okay. So this prints the line, this line prints the string hello world with a new line character to the console. All right. What is this std? I'm calling it standard. Some people call it stud. Some people call it std. I call it standard. So standard is a namespace. We'll have more on namespaces later, but just think of a namespace as like if you have a bunch of code that you've written, say for a library, and in Java you might say like library dot function name. Here you can say namespace : So there's a namespace called standard, and in that namespace there's a whole bunch of functionality. Okay, we'll get into more of that later. Inside that namespace, created for you, is this cout output stream. Okay, so cout is a variable that lives in the standard namespace. It is a stream, and this is called an operator. So an operator, just like plus or just like minus, okay, this is an operator that sends. The cool thing about this is that at first the syntax is a little confusing, but my intuition is that whatever is here gets sent that way, left, to this variable. Okay, so this is a binary operator. Someone said that this : is called the scope resolution operator. Yes, I'm trying not to overload with too many details, but yes, this talks about the scope, and the scope of this is within that namespace. And so you can think of this as piping that string into this variable. And as long as this variable knows how to deal with this operator, which we'll get into later, it will do its thing. And the thing that standard cout does is send it to the console, okay? And this can be used to print any base C++ type, so as well as strings. So if you've got a string, if you've got an int, if you've got a float, you can just print those out to the console. And if you define your own class and you want it to be able to print, you can actually define what this operator does within your class so it can be printed out to the console like this as well, okay? Just similar how to Java has a toString method, and when you print it, it uses the toString. This is the same sort of thing. And of course, each C++ statement must end in a semicolon, okay? So we've got a semicolon at the end. And be very careful that C++ is case sensitive, okay? Just like most programming languages, it is case sensitive. At the very end, we have a return 0. Main, as we said, has a return type of int. But you'll say, this is main. Main doesn't get called by any other function. Why do we have a return type? But it turns out that main does have a function that calls it, and that's the system. The system calls main, right? And so the system wants to know, hey, program, did you work okay? Right? Java will take care of that for you. C won't take care of that for you. So essentially what we do is if we've reached the end of our program successfully, we return 0. And that tells the operating system to inform the user that everything ran smoothly, okay? If you want to, throughout your program, you could say if you were trying to read from a file, for example, and you didn't find the file, you could say return -1 or something like that. You could have an error code that you return. And so you return something else if there's an error, and that is used by other programs to detect errors, okay? So you can return whatever you want, but basically we're only going to be returning 0 in this course because we're not getting into like systems programming and stuff. The program may compile and run without this return integer, but it's highly recommended. Just return 0 so the system knows that you're okay. All right. Whitespace in C++. If you're coming from Python, this is going to look like a disaster. But if you're coming from Java, you're already familiar with this, right? For the most part in C++, whitespace doesn't matter. You can put as many spaces as you want between things. Now, of course, if you have a variable name, you can't put a space between the C and the out here, right? Your strings and your variables all have to be, they have to be formatted correctly. But this line is equivalent to this line, is equivalent to this line, is equivalent to these two lines, right? For the most part, it doesn't matter. Even with functions, right? You can put the brackets in any places that you want. Now this would, it would be kind of ugly if you did it in some of these ways. However, there are some exceptions. And the whitespace exceptions for C++ are, now this is not all of the exceptions, but it's a couple of them. You cannot separate strings by a new line. So if you wanted to print out hello world, oh, give me 1 second here. Apologies for this. I've got some notifications going on in the background. I just want to turn those off in case you can hear them through the... Alrighty. We are back. Okay, so whitespace. Whitespace, yeah, so strings cannot be separated by new lines. All right, so this will not work. This will actually not compile. And comments cannot be separated by new lines either. Okay, so // that's a comment. You can't do a single line comment across multiple lines. You can have multi-line comments. There's another syntax for that, but a single line comment cannot be separated. And there's a couple of more, if you really want to go down in the weeds with the whitespace, you can, but all right. Indentation and braces. I know that this is a religious argument and I am not trying to evangelize or convert, but one of the things that happens when you are programming for a career is that when you go to a company, you have to conform to their style, because no particular style is correct and no particular style is incorrect, but the incorrect thing to do is to mix styles. Okay, so if you come from Java, JavaScript, a lot of other programming languages, this is standard. Okay, this is the K and R variant of braces, where you have a block of code and the thing the open bracket is on the same line. Almond, okay, is when your bracket starts on the next line. I particularly enjoy almond style when it comes to C++. I actually have reasons for why I like almond style. We will be using the almond style for our assignments in this course. Now, you might say, oh my God, I can't read code like that. Okay. I understand. I came from here. I did this for 10 years. All right. Until I saw this. And I know that it adds an extra line to your code, right? Not as efficient, whatever. However, when you're doing algorithmic programming, like I do a lot, sometimes you get some nested loops, some nested ifs, stuff like that. And when you can visually match the closing and ending of a function or a block of code vertically like this, it actually kind of works wonders. And I find this type of code, while it is more compact, it's a little bit more difficult to read code in this style than in this style once you get used to this style a bit. So that's all I'll say about it. I know that there are people out there who will have valid reasons for using this as well. And when I use JavaScript, I still use this style, so I understand. But in this course for C++, we're going with the almond style. And I will just I'm not going to be a huge stickler about it, but I will be telling the TAs, look for almond style and just ping them 1%, maybe 2% on an assignment just to get you into our style. Okay, so we're going to be using almond style. The C++ standard template library is a collection of classes and functions available within the C++ language. So C++ has a bunch of libraries that come with it in the STL. They are like Java's libraries, right? You have to include them and then they do some cool stuff. So if I want to use a string I've got to include that somehow. If I want to use a vector, I got to use that somehow. If I want to read from a file, I've got to include that somehow. And all of that lives in the standard library. Now, the standard library doesn't do things like graphics, right? So that's why in this course, our only external library is going to be SFML, which is a simple, fast multimedia library, which allows us to draw things to the screen, load images, and do mouse and keyboard handling, because that's the only thing that we need that is not handled by the basic library. So STL, for example, has strings, it has input, output, it has streams, files, it has a bunch of containers, it has algorithmic like sorting, min-max, shuffle, it has container functionality, we can fill a container, we can erase things and stuff. So all of that is in the STL, and I'll show some examples of that. You must include whatever library you're using in your C++ program, and these are referenced via the standard namespace. So it's called the standard library, standard template library. We'll talk about templates later. And so it's in the standard library, and you wouldn't want to have to type standard library dot whatever, right? So they just said standard. So that's the namespace, and so you say standard string, standard vector. So namespaces, as I said, I was going to talk about this a little bit more. They encapsulate code, right? So it's just like the scope of the code is within this namespace. So for example, if I had a namespace and I had some variables in there, let's say I had some physics namespace, right? If I wanted to store a bunch of physics variables, like the acceleration due to gravity, or some constants out there, like a bunch of constants, right? Maybe what I'd want to do is create a namespace for those, so that when you went to look for those constants, you'd know where to find them. They're in that namespace. So for example, if I have a Dave namespace, I would say namespace Dave, and I would encapsulate that by brackets, and then I would put my variables in it. So for example, if I have an int, I'm going to call it ivar for intvar, and that's equal to 10, or I could have float gravity equals whatever 9.8 meters per second squared. If I want to reference that later, I can say Dave : ivar. So this : just says look it up within that namespace, or that scope of the code, and get us that. So the things we will be seeing in this course, by far the most often, will be standard string, standard vector, and standard map. Okay. Now, I'll get into using namespace standard later, but we're not going to do it in this course. I know it always comes up. All right. C++ source code. I've talked now about like the high level details of the language. Let's get into some code. So the code of your program is written in files. Now, the compiler really doesn't care what the extension of your file is, right? As you get more familiar with computers, you know that it's the content of the file that matters and not the actual extension, right? So you can write source code in any extension that you want. However, there are standards, right? There are conventions, and we're going to adhere to those conventions. So program code is going to be written in .cpp files, okay? Now, Java will enforce you to have them in .java files. C++ does not enforce you to put them in .cpp files, but I am enforcing you to put them in .cpp files. So for example, we will have main.cpp, right? That'll be where our code is. And we'll have a bunch of different files for our assignments, but I'll talk about that when we get to the assignments. You may see in older legacy code bases, these are, sometimes it's .C for C++ code. .c conventionally is C code, not C++ code, or .cpp. We're going to be using .cpp. All right, it's lowercase. That's what we're going to be doing. If you go work somewhere else, just conform to whatever they do. It's not hard, right? And CPP code is used for function and class definitions. All right. So now comes the biggest change between Java and C++ in terms of managing files and code, is that we also have in C++ header files. So there's code files, program code files, the .cpp files, and we also have header files, .h files. And these are used for function and class declarations. So declarations versus definitions, when I get into the when I get into the live coding, I'm going to show you a good example of that, and I'll have an example in the slides. But just know that there's a difference for now, and we will get into it. All right. But first, I want to talk to you about the C++ compilation process. All right. So C++ programs are compiled into binary executable files that are run directly by the CPU. So there's no virtual machine like Java. When you compile Java into a class file, it's actually run by the Java virtual machine, okay? And if you run Python code, that is interpreted on the fly by Python. If you run JavaScript code, it's interpreted by the JavaScript engine. So the fact that it's actually compiled into a binary, which is directly readable by your CPU, that is advantageous because it usually results in faster execution, but at the price of usually lower level programming, right? But we'll show you in this course how modern C++, it's actually pretty high level programming. There are many, many different C++ compilers for many different operating systems. We'll talk about a few of them in this course. Now, the full process by which C++ goes from source files to executables is a little bit complicated, okay? But I want to explain it to you because it is necessary to understand this, at least at a basic level, in order to interpret and fix errors that you might have that you come across in this course, okay? And in your C++ career. So here, up here it says sourcecode.c. That's because I stole this from a website that does C programming, but the process is exactly the same for C and C++, okay? Now, exactly, okay, with a little difference, but for all intents and purposes, it's the same. The very first thing that happens is that all of your source code and all of your header files are run through the preprocessor, okay? So all of your header files and all of your source code files go through the preprocessor. And the preprocessor does things like include whatever, okay? Define pi 3.1415926, whatever. So any preprocessor commands that you have in your code, the very first thing that happens is that it says, okay, run it through the preprocessor. Now, there could be errors at the preprocessor level of this stage, okay? So for example, if you said include this file and the preprocessor can't find that file, then that is actually an error that's thrown at the preprocessor level. So it hasn't even started to compile your code yet because you said, hey, preprocessor, go grab this file and include it for me, okay? So one stage of possible errors is the preprocessor stage. Once the preprocessor has run, essentially what the preprocessor does, it's a big find and replace tool, okay? So if you say include math.h, what that command literally does is it goes and takes math.h, copies it, and puts it right there in your program. It literally copies the whole file, okay? So what happens then is after your source code and your header files are preprocessed, the preprocessor spits out an expanded source code file, right? With all of those libraries that you included at the very top of your program or wherever you included them. So then you've got a huge source code file, and that is what gets spit into the process to the compiler, okay? So the preprocessor output is run through the C++ compiler. So now you could have an error at the compiler stage, right? So for example, a compiler error might be trying to reference a variable that isn't there, right? Or trying to declare an int as a float or something like that. Or your function has the wrong syntax, right? So syntactic things and a bit of semantics, but mostly syntactic things will happen at the compiler stage, right? Not the preprocessor stage. Once your compiler has run, then object files are created. So if you've ever used Java and you've compiled a bunch of different Java files, right, into a bunch of different class files, that's kind of like what an object file is, okay? Each of your .cpp files is going to produce a .o file. And so that's what this stage is. The object files are created. And then the linker is run, and the linker is going to link the object files together in order to finally produce the executable, okay? So again, Source code and header files go through the preprocessor, it does its thing, creates an expanded source file, which is then compiled. The compiler creates object files, and the linker links all the object files together. Boom. Now, I know that that sounds like super complex, but it's basically going to be done for you. You can do all of this in a single command, okay? And if you just type like G++ my program, all that is done for you. However, this is the actual process because a linker error is going to have to be fixed in a different way than a compiler error, right? So once we get into the course, I'll show you some examples of those and how to fix them. Alrighty. So the G++ preprocessor function, I think I meant to say C++ here. So the preprocessor functionality that I talked about, the preprocessor runs all specific preprocessor directives. So what is a preprocessor directive? Well, most of the ones that you'll see are either includes or macros, okay? So for example, if I want to include a library that's included in the system somewhere, I would say include library. Or if I want to include a specific file that is not in my system library, I would say include specific file. Or if I want to define some constant, like this limit, 100, or I can define these very simple macros here that are kind of like functions, but not really like functions. These are preprocessor directives, okay? In this course, we will only be using the first two because these are quite dangerous and there's other ways to do them in modern C++, so don't worry. If we ever say include X, this inserts file X into the file. Like I said before, it inserts the entire text from myObject.h into the file calling the include. Now, turns out that it will usually only do it the first time you call it. If you say it twice in a row, we have some things to prevent it from including it multiple times, but it will just include that text there. Alrighty. The C++ compiler. There are several popular compilers that are used on different operating systems. So on Linux and Mac, I would recommend one of the following if you're using Linux or Mac for this course. Either the GNU C compiler, GCC, which has C++ support, so G++, or Clang, okay? Clang has a LLVM and all this stuff I'm not going to get into, but basically these are the two compilers that I would recommend. Just use G++, it's fine. In Windows, there are different compilers in Windows, but please only use Visual Studio if you're doing this for Windows, okay? Windows is a nightmare to set up C++ compilers in, except Visual Studio. If you want to set up anything but Visual Studio in Windows, it's a goddamn nightmare. Trust me. I'm saying that MinGW exists, but for the purposes of this course, it doesn't exist. All you have to do for this course, we'll get into this in assignment 1, is install Visual Studio, double-click the project file, and hit compile. That's it. Please don't do anything else for Windows. You're just putting yourself through torture. Visual Studio will actually do the same things that we've been talking about behind the scenes, but it does it kind of transparently, right? It controls the compiler, it controls the IDE, it does all that for you behind the scenes so you don't have to worry about it. That's the great thing about Visual Studio. But it's still important to know the entire process because inside Visual Studio, if you get a link error, LNK error, you got to know that that's a linker error. So it probably means that a library was misspelled or something like that. If you get a compiler error, you need to know, okay, that's probably a syntax thing, right? So you still got to know what the process is. All right. So if you want to compile an actual C++ program, what are you going to do? Well, let's say we have a program written in myprogram.cpp. We're going to compile out the code into an executable, right? So we can say G++ myprogram.c++. That's it. So all that whole process that we just talked about for 10 years is just that. We type it and it does it, right? It does it for us. And that is going to produce an executable file called a.out. Why that's the default program name, I don't know. But I guess it's A is the first letter, .out means it's the output of the compiler, but There it is, a.out. That's a terrible name, so let's specify a program name, okay? Someone asked about VS Code. No, this is very important. Visual Studio is not Visual Studio Code. There is one program that is called Visual Studio. It is a huge IDE by Microsoft that includes a C++ compiler, debugger, all sorts of great tools for C++. It's called Visual Studio, okay? I know it's confusing, but then there's this other thing that is called Visual Studio Code. It is a separate program. I don't know why they did this. I guess to save on branding, but VS Code or Visual Studio Code is not Visual Studio. It has nothing to do with Visual Studio. It never had anything to do with Visual Studio. So, Visual Studio, do not use VS Code if you're on Windows. VS Code, you can use it if you're on Mac or Linux to edit your programs. That's fine. It's a text editor with plugin support, right? It's not a compiler. So VS Code, not a compiler. Visual Studio is a compiler. I'm going to get 10 emails about that, so I've got to repeat it. All right. Back to this. We've got our a.out. It's terrible. We don't want that. So let's specify the output file name. Okay, so I can say g++ myprogram.cpp -o myprog. Okay, so my program. And then if you're in the console, you can run that with /myprogram. All right. Now in Windows, you would just hit compile and run, and it would compile it and run it for you. Or you would double click the executable. All right. But if you're on the console, if you're using Mac, if you're using Linux, you're probably going to be using the console. So you just run it like that. And then if you had any arguments, remember our argc, you would type my program, argument 1, argument 2, argument 3. All right. If you want, you can get fancy with the compiling. So if we want to actually view the results of what the preprocessor did, we can do that with -e. Okay, so g++ -e myprogram.c or .c++. And then you say, well, this is a command line thing where you pipe it into another file. Okay, so the output of that will either print to the screen or you can put it in a file. All righty. Someone asked, is the executable the same as the binary? Yes, for the purposes. So a binary file, typically, the definition of a binary file is something that's in a binary format that is not human readable. But when you're talking about the compilation of a program, the resulting binary is interchangeable with saying the resulting executable. Okay? Technically, not all binaries are executable, meaning that they can be executed and run as code, but we're using them interchangeably for this. All right. So, just 1 second. If you give me 1 second. So someone in the after last class said that they wanted to see George again. George just visited. So say hello to George. George is an expert at C++. He has 4 years of C++. He has 3 internships. But he got fired for sleeping on the job. So, all right. So I'm going to let George down. I'm going to keep typing here. So we have... that's the favorite part of everyone's lecture is seeing the animals, I know. All right, so he's the TA. No, he's not the TA because he's too expensive. I can't afford him for the TA. I should pay him to sleep, yeah. By the way, because this is like the tutorial lecture, I want to give you as much information as possible. I know that some people are just going to skip this, so this lecture is going to go a little bit long, okay? But I want to give you as much information as possible, and like, you know, we got time, so I can say... Okay, George is actually back there messing with some hardware, so I'm just gonna put him out of the room. 1 second. So we'll say hi to George once more. Say goodbye, George. I love George. He's awesome. He was named after George Costanza, by the way, because he's a little bit of a big ferret. All right. I'll be right back. Okie dokie. George is very happy to have met you as well. All right, so if we want to specifically compile to an object file instead of directly to the executable, we can do that, right? And it turns out we may have to do that when we get bigger and bigger programs. And so you'd say g++-c myprogram.c, and that will produce myprogram.o. And then you run the linker, which is actually the same program. You say g++-o myprogram. So that says run the compiler, but link these object files together. So the G++ does everything for you, okay? And depending on the file that you specify, it will know that, okay, this is a source code file, or it is an object file, and it'll do the correct thing. Okay. Now, in this class, I'm going to give you a make file, and a make file is essentially a configuration file for G++. I know it's not, but essentially it is. And all you'll have to do in this class is type make. All right. So multiple files can be compiled in one step. If you want, you can compile all of your CPP files, and it will not generate the intermediate object files. However, if you do it this way, it recompiles every CPP file each time. And you might not think that that matters, but once you get into, like, you know, actual retail code, or if you're in industry or something, if you've got thousands of CPP files, it's really expensive. Like, it takes minutes, if not hours. I know someone who worked at Facebook and it took like 2 hours to recompile everything, right? So ideally, you don't want to compile all of your files every time. And one of the great things about the linker, even if it is a little bit complicated, is that if you've only changed a couple of your files, then you only want to recompile the things that you've changed, because linking is much faster than compiling. So ideally what you would want to do is only compile the files that have changed since the last time you compiled, and generate the new object files if there are CPP file changes, and just link them together. And so this can be done with a number of different systems. In Mac and Linux, you're going to be using the make file that I give you. This is automatically done by the project file in Visual Studio. Okay? So again, just as a breakdown, that's what it is. Source code goes through the preprocessor. Output goes through the compiler, and the object files go to the linker. Someone asked, are object files binary files? Yes, they are. They are binary files, but they are not executable. Okay? They are intermediate output binary files that are then linked together to form the executable program. It's a good question. Alrighty. So the separation of CPP and H files. I mentioned this briefly before, but why do we do this? A Java file just has all the code there, right? Why do we do this in C and C++? So C++, oftentimes when it comes to class code, is often separated into two files. The header file with the declarations, and the CPP file with the definitions, or the implementations. So a declaration is something like this. A declaration says, hey, a function that takes these inputs, has this name, and has this type of output, it exists. Okay? So the function sum, which takes in two ints, x and y, and returns an int, that function exists. That's what this file is saying. That's what this line is saying. It's a declaration. I declare bankruptcy. No, I declare int sum in x. That's a declaration. A definition is the actual code of the function. Okay? So what the function actually does. So it would be int sum this return x plus y. Now, that's the definition. That's the difference between a declaration and a definition. Okay? Header files. They contain class or function declarations. Declarations include the function name, return type, arguments, etc. It is required by C++ to see all declarations of all classes, functions, and variables before they are used. Okay? That means before in the file. So if at any point you scan from top to bottom in a file, I'll give an example of this in the live coding. if you see a variable or a function that didn't appear literally above it in the code, it won't be able to do anything with it. So these serve several useful purposes beyond just the required declarations. So I'll show you what that is for now. All right. So say we are at some point in our code, right? And we've got this function. And inside this function, we have an object called myClass. So we have a class that we've written somewhere. I don't know where it is right now, right? But I have a class. And inside that class, I have a function called doSomething. If this is all that you see in your program, we can't say, okay, myClass C, because my function, oh, sorry. That last part, just ignore that. Say we have our function somewhere in our code, okay? Now what we have to do is we have to write our class myClass. Where are we going to put that in our code? Let's say all of our code had to be in one file, right? Let's just say that it had to be that way. So we actually, let's say, oh, I kind of want that class to be at the bottom of this file because I don't want it to be up at the top. I want more important stuff at the top that I'm going to be editing more often. Well, it turns out that you actually can't define your class below where you reference it in the code because the function can't see it yet. The compiler goes from top to bottom. It's real dumb, okay? And if it hasn't seen myClass yet, it doesn't know what to do. So you have to define your myClass above where you call it, right? So you could define it up here. So it gets real annoying defining all of your classes in the same file, all right? So what you have to do, or what you should do, is whenever you declare a class, like whenever you have a new class, you put it in its own file, right? And then in order for this function to be able to see it, what you would do is you would include that class here. So if you've got all the code for your myClass object in myClass.h, then what you would do is somewhere above this myClass, you would include myClass.h. And remember what the include function does? It literally takes all of myClass.h and inserts it into the file here. So it's kind of like the compiler thinks you typed it in all there because what the preprocessor does is it takes that file and it puts it there, okay? And so some people in the chat out there are giving really specific technical names for stuff. I'm not going that deep, so I appreciate you giving more information to people, but there's a little bit of information overload and I don't want to give that. Now, in any other, almost any other programming language, JavaScript, Java, etc. No, don't apologize. I just can't. I'm not going to mention everything that's said in the chat. That's all. But thank you for giving the information. I just wanted to let you know why I'm not saying everything that's said in the chat. But a good point is that in other languages, it would let you type your myClass down here, right? It would let you type another function down there. That's because their compiler does a number of passes through and resolves all of those things. If it didn't see it the first time, it will see it the next time, okay? So other programming languages let you do that. C and C++ do not let you do that. But using header files, it'll be fine. We won't need to worry about that. All right, so some of the benefits of header files. Here is an actual class that we're going to be writing in this course, okay? This is the vec2 class, and it has an x and a y and a bunch of functions. So what are the benefits of header files? They allow you to see the entire functionality of a class at once, right? So these functions here, these are function declarations or definitions. Someone answer out there in the chat. Are these declarations or are these definitions? What goes in the header file? Perfect. All right. They're declaring that these functions exist. So these are declarations. Everybody got it right. So if I look over here, I can see at a glance oh wow, okay, so this class has an X and a Y in it. It has a couple of different constructors. It has an equals operator. I can add, subtract, divide, multiply. That's cool. I can see everything about that class on one screen. It's a huge cognitive benefit, okay? Reduces cognitive load. I don't need to scroll. I don't need to remember when I can see everything. It separates design from implementation. That is a big deal when you get into large software projects, okay? This is the design. Now, of course, there's a little bit of implementation in the actual declarations, right? But this is basically the design of the class. And then in the CPP file, we would have the implementation of the class. So we know that two vectors can be added together and they give us a new vector, but how does it work? How does it do it? Well, if you want to know how, you go to the CPP file. And the cool thing is that headers seldom change, leading to less files being recompiled, okay? So that would mean that once we get the declarations down for our class, if the implementation ever changes, and this is such a low-level detail that you probably won't get unless you've done a lot of C++ already, but basically by separating things into headers and CPP files, since declarations very rarely change, but implementations frequently change, then we are recompiling fewer files because the files are going to be including this header. So just a bit hand-wavy. All right, the drawbacks of header files. More files in your code base, right? Despite what some would have you believe, more files is always worse than fewer files. Now, I'm talking about that purely in terms of files. Of course, if you have one 2 million line file, that's horrendous. That is not necessarily better than having 20 100,000 line files, right? I'm not saying that a one file program is always what you want, but of course, having more files is just harder to manage, right? So if you view more files as a drawback, then of course that's a drawback. And what that means is that it can be a little bit annoying tabbing back and forth between header files and CPP files and stuff, but you get used to it. Cyclic dependencies can be hard to detect and resolve. So a cyclic dependency, we will be avoiding them in this course, but just be aware that when you do your own C++, let's say you have a class A and a class B. If class A stores a class B and class B stores a class A, that's a cyclic dependency. So if one class depends on another class and the other class depends on it, sometimes that can happen. So for example, let's say you have a student class and a course class. So you're writing some data management system for the university, right? Your student class might want to keep a list of courses the student is taking, right? So you've got a list of courses. However, your course class may want to keep a list of students that are taking the course, right? And so there are little tricks and stuff that you can use in C++ to resolve these cyclic dependencies. We're not going to get into that because I'm teaching you just enough to learn, to be able to do this course. So just be aware that that can happen. Okay. Some people say that that only happens due to bad design, but I say that's not true. Usually it's because of bad design, but there are some times when it is unavoidable that you need to have references back and forth. All right. Then we get into things like forward declarations and, okay, we're not going to be going that far. All right, so here's another diagram. We've already talked about this. Every file goes into .o file and then gets linked together. All right, primitives. You all know these. You've all done Java or some other thing. There's a bunch of different types, right? I'm not going to go into them all. This is just for your own reference. Different arithmetic operators. So things that may not be in other languages. So for example, integers have this modulus, remainder, integer division. You can add and subtract. You can pre-increment or post-increment, pre-decrement or post-decrement. This subtracts one from a number. This adds one to a number. We've got bitwise operators. We may get into bitwise stuff that's really cool later that may not be in other programming languages. Don't worry if you don't remember all that. Okay? I don't remember all that stuff all the time. You're not going to remember all that stuff all the time. You're going to be Googling stuff. And I know that in the first lecture, I went on this huge tangent about, don't Google stuff. Well, you're going to Google stuff. Like, you need to, you're going to remember syntax. Just don't Google solutions to the assignment. That's what I'm trying to say. Functions. We've got a return type, then a function name, then some arguments, and then some logic. It's basically the same thing as Java. We can have the same function names with different input arguments, but you can't have functions with the same name that only differ in return type. Okay, so just keep that in mind. C++ classes. Here is the syntax for declaring a class. So we have a class point. Sorry, let me get my thoughts. This is how you declare a class. You say class and then the class name. Then you encapsulate the class in brackets and you have to end with a semicolon. How many times have I forgotten that semicolon? It's crazy. So here would be the header file contents, the declarations of my class point. I've got two variables here. My class point is going to have an X and a Y because a point in space is an X and Y location. Anything that you do not declare the scope of is by default private. So the syntax I like to use is I'm going to say public down here, and everything that's public is below that, and anything above that is private. What some people do is declare public variables first and then specifically declare private variables later. It doesn't matter. It's just style, okay? So this is less typing, so that's what I do. And in this course, I am using, I can't remember what the name of this is, but the syntax where this m underscore, so this is the X variable, right? In my class, m underscore refers to a private member variable. So wherever you are in your code, you know that, oh, this variable is a private member variable. Can't remember what the exact name of this style is, but it doesn't matter. We're just using it, okay? So if this is the, and you'll see why that matters later and why local variables, yeah, it might be Hungarian notation, someone in the chat just said. So this might be Hungarian notation, but it allows you to tell the difference between locally scoped variables and class scoped variables. All right, so this is the declaration. Somewhere in the CPP file, I would have the implementation. Here is how you do a constructor. So I would have a point class. I would say point, the point constructor, the input variables to the constructor, and then I would say, oh, I'm going to set my private member variable of X equal to the input variable of X, and the private member variable of Y equal to the input variable of Y. Now, C++ has a cool way of doing this. It may not look like it, but this is an inefficient way of doing this. The reason for that is because whenever you call the point constructor, whenever you call any pointer or any constructor in C++, all of the member variables are given their default values, right? So here, if I did a constructor like this, I would have a constructor called point, and as soon as I got into the code, the X and the Y would be given their default value of 0, which takes some amount of time, some amount of cycles. And then by doing this, I would be overwriting those default values of 0 with the X and the Y. Okay? Now for integers, this doesn't make a huge difference, but for some things, for some larger data types, it would make a big difference. And for the amount of points that you're creating, you're essentially doing double the work here, because it's giving the default values of 0, then it's overwriting with X and Y. So what we want to do is the syntax called an initializer list. And an initializer list has a weird syntax if you come from other programming languages, but essentially, after the point constructor is declared, you have a semicolon, and just remember, all of this white space is me. The white space doesn't matter. You could have this come right after it or all on this line or spaced out. This is all just white space, but I find this white space is easier to mentally process. This initializer list says that even before we get to the code of this, set up these variables. So mx gets the value of x, my gets the value of y, and they will never be given that default value of 0 with the initializer list, so we've cut out half of the assignments. Okay? It's such a small detail, but just realize that that is what you will be seeing in this course, is this initializer list, because it's the most efficient way, it's the correct way to do it. Also, something to realize is that if these private member variables were const, meaning constant, they can't change, then if that was const, this would throw a compiler error because you cannot set the value of a const member variable. However, you can set the value of const member variables using initializer lists. So wherever you want to have a const member variable set via the constructor, you have to use initializer lists. And then, of course, we have a destructor as well, and anything you would want to do cleanup. Maybe you had some pointers in the class, you want to delete the pointers, whatever you would have here. Quickly, we'll talk about the STL. There are very commonly used containers in the STL, standard vector of type T. So there's some, I don't even know why I have this here. So standard vector of T, so for example, you can have a vector of ints, a vector of floats, a vector of any custom data type as long as it has a default constructor. You can have a set. This is an ordered set, so it makes sure there's only one of something in a set. You can also have a map, so you can have a map of strings to ints or whatever you want. Here's a reference for like how to use a vector. I'm actually going to do some live coding, so I'll just leave this here for you. It's in the notes. I'll show you how to do this in the live coding. All right. So officially, our time is up for the class, okay? But because this is like, I want to give you the best education possible. So what I'm going to do is I'm going to do some live coding now. So if you want to come back later, if you have another class, I completely understand if you're watching this live. The cool thing about watching lectures that are recorded is that you can watch them at double speed. I'm not done. This is not the end of the class. I'm actually going to do a bunch of live coding now. So for people who are very new to C++, I just want you to give you as much information and as much teaching as possible. So what we are going to do now is we're going to do some live coding. And like I said before, I have not practiced this beforehand, so we'll see how this goes, okay? So let's get started with some live coding. Now, I'm going to be doing this live coding in the terminal. The reason I am doing that is because it's just easier for me. I'm really used to it. And for the purposes of what I want to show you, it's the best thing to do, okay? So I'm in the terminal here. I'm going to be using Vim to show you some things. So what I'm going to do is I'm going to have vim lecture2.cpp, and this is going to open up a new file called lecture2.cpp, and we're going to just do some coding in C++. So I realize that this lecture is long, but it's for your benefit. There's no textbook, so just watch this if you want to. You don't absolutely have to keep watching, but if you're new to C++, this might be pretty fun. All right. So what we're going to do is we're going to type in our, oh, and by the way, if you want to follow along, if you are a student at the university, the way that I am doing this through a terminal on Windows is I'm using a program called Putty. You can also use Windows Terminal. And you can SSH into our department. So using your CS username and password, you can SSH to garfield.cs.mon.ca, so P-U-T-T-Y, Putty. And then you type in your username and password and you get this exact terminal. It has a C compiler, so you can do exactly what I'm doing from Windows if you want to practice your C++. So we are going to include IOStream, and I'm typing all this from memory. So give me a little break. If I make some mistakes, we're going to make the mistakes together and it'll be fun. All right. So I've got int main, right? I got to type that in. I've got my int argc, my char star argv, and then I've got my, let's see here. I've got a microphone between me and my keyboard, so it's a little hard to type. So we're going to return 0. And up here, we are going to do standard cout hello world. And and then I'm going to do standard ENDL. So I know we didn't do this in the slides, but it turns out, annoyingly, different operating systems have different new line carriage return characters. So typically you would just type a /n, but if you just type /n and then you open it up in Windows Notepad, there will be no new line. It's really annoying. And so what this standard ENDL is this compiler is built for this specific operating system, and so it will know the special end line character. So what we have to do here is I'm going to exit out, so right quit, and then I'm going to type G++ dash standard equals C++ 17. That is the standard that we are using for this course. lecture2.cpp. And then, unfortunately, my head is in the way, but, so it's just going to, this is going to compile and it's going to go to a.out. Okay, so it's compiling. And now if I run /, that's the run, a.out, it's going to say, hello world. All right. Now, if I wanted to compile to my own program, I would say -o. Oh, let me, one second. Let me make a few new lines so my head isn't in the way. I would say -o, lecture code or something like that, right? And it would compile it to that. And then I would say / lecture code, and it would run the same way. All right. Now, it's going to be really tedious for me to have to exit out of Vim, retype everything every single time. So what I've done is I'm just going to go back into the lecture code. I have a macro in Vim which does that. So I have a macro in Vim. I just hit Control B is my macro. What it does is when I hit that button, it will save the file. It will compile the file. If there is an error, it will show me the error. If there is no error, it will run the program. Okay? So from within Vim, if I just hit my macro, it'll compile it and run it. So that's what we'll be doing from now on. But just realize that, if you don't have that macro set up, you'll just be typing in G++ whatever. I just have that set up here. So there you go. So if I do type an error in here, so for example, if I type in clout instead of cout, and then I do that, what will happen? All right. So here is your first C++ error. My head's in the way, but I'm not going to move that, unfortunately. So it says in function int main, here's an error. Clout is not a member of standard because I said standard : cout. And it says up here where you can't see, it says, did you mean cout? And so it says that, right? So it suggests change clout to cout, right? So I do that. I change clout to cout, I recompile, and it works. All right, so sometimes the C++ compiler is very useful. Sometimes it is not very useful. All right, so let's do something a little bit more complex than this. Let's do some int variables. All right, so I've got int A equals 42, int B equals 10. All right, so how would I print out some integers to the screen? Well, the cool thing is I can just type out A and then maybe a space between them and B, right? So anytime I want to type a new thing, I just pipe it back in. So everything gets piped into cout. I compile and run. I get 42 and 10. If I wanted to say do some math here, then I can say plus and put that in parentheses, and then that should print out, well, what? Okay, 52, right? Now let's say, let's erase this, and let's say, all right, int age equals 39, because that is how old I am. Now, let's, I could do doubles and floats and all that kind of stuff. You know all about that. Let's use standard string. So standard string, first name, I'm going to say that that's Dave. And standard string, last name, that's going to be Churchill, right? Okay. Oops. I've been programming too much Python recently, so I got the single quote disease. All right, so I'm going to print out first, and then I'm going to print out a space, and then I'm going to print out last. All right, let's see what this says. There we go, Dave Churchill. If I want to have a string, standard string, name, then I could say this is first plus a space plus Churchill. So we can, or not first plus last, sorry. And then down here, I could just print out name, because modern C++ lets us add strings together. It's pretty neat, right? We're not messing around with chance, char star, etc. All right, so let's say, now, here is something you're going to hear or see online, all right? You're going to see this, using namespace standard. What this tells the compiler, this is a contentious topic. What this tells the compiler is that we are going to be assuming that we're using stuff from standard. So if there's ever anything that I type that you don't recognize, assume that it comes from standard. What that means is, when I have using namespace standard, I can do this. Okay? So I don't need to put standard in front of everything. People like that. People like not having to type that. If I come up here now, and I erase that, and I compile again, it says cout was not declared in this scope. I don't know what a string is. Oh my God, what's happening? And it's because it doesn't know that it's the standard version, right? So in this course, we are not going to be using namespace standard. I know that it's a couple of more characters to type, but I prefer it because it's more verbose and it says exactly what we're doing, okay? So we are not typing using namespace standard in this course. If you do, we'll ding you a few marks on the assignment. Okay, now what we're going to do is let's use a data structure, okay? Let's use a vector. So how would we use a vector? Let me delete everything I have here. Let's say, all right, I'm going to have a standard vector of integers, right? A standard vector of ints. I'm going to call this my vec. There we go. So I have declared a standard vector of integers. Now, in order to add something to a vector, I would say vec.pushback, because you're pushing it to the back of the vector. Vector is a Q data structure, right? Sorry, it's a stack. I guess with push and pop, it's a stack. Ignore that. It's not a queue. It's not a stack. It's just a vector. So we're going to push back 42, vec.push back 10. We're going to do what we did before. Now, I could say standard cout vec 0, right? And then maybe a new line character. I'll be lazy and just do that. And now I'll copy and paste that, and I'll say vec1. All right, now let's see what this does. Okay, so it printed the first thing in the vector, and then it printed the second thing in the vector. Now you might be saying, ooh, what if we said vec2? Because in Java, we'll get a array out of bounds error for this. Let's see what happens. Uh-oh. But the vector isn't that long. So what's happening? Here is where C++ gets very interesting. You're on your own when it comes to vectors, okay? When it comes to arrays and vectors, if you go beyond the scope of a vector, unless you're running in debug mode, you're just getting whatever happens to be in memory at that location. So be very careful when you do that. Now, if I had 30 things in my vector, I'm not going to want to have to write like a specific print statement for everything in the vector. So let's talk about how we go through the vector. All right. So there's a few different ways to iterate through containers in C++. We could do the standard thing where we go for int I equals 0, I less than vec.size, I plus plus, and then we can say standard cout, oh geez, I keep typing that, vec I, and then a new line. Okay, so let's see what happens here. All right, so it did work. It did work, but it gave us a warning. So there are warnings and errors. Let's see what the warnings said. It said, warning, comparison of integer expressions of different signedness. Int and size type, aka unsigned int, or long unsigned int. So what that warning told me is that the vector size is an unsigned integer, and the integer I is a signed integer. So if you store, you're all familiar, you're fourth year computer science students, there could be some error in the logic if I'm comparing signed integer and unsigned integers. So whenever I'm doing a loop through a vector, I'm going to use a size type or size t. On different systems, this size t is essentially a long unsigned int. However, size t is what is safe to use because it will, on a 32-bit system, it will be 32 bits. On a 64-bit system, it will be 64 bits. So now I can do this, and there's no more warning. Okay? So just a rule of thumb is whenever you're iterating through a vector, its size is going to be of type unsigned, so use unsigned. All right? Now, if I add another thing to this, of course, it's going to loop through my vector, and it's going to print all three things. Okay. There's another way to do this, and that is a range-based for loop. So I can say for, now I need the type that's in my vector, right? So I'm going to say for, this is int a in vec standard cout a and a new line. So what this does is it says for everything in the vector, assign it the name of a, and then I can do something with it. All right? So let's look at that. And it did it. So it printed out the first thing the first time, and then the second thing the second time. However, let's try this now. So if I delete this, and I go up and I make this a float vector, and I make these floats, so I'm just going to declare them as actual floats. Now what happens is I'm taking the vector, I'm converting everything in the vector to an integer, and then I'm printing it, right? And so be careful when you do that. So there's a really cool thing that you can do in modern C++ is the auto keyword. The auto keyword is going to say, hey, whatever type that is, make it that type. So even though it's a signed, or it's a statically typed language, I could either say float a equals vec1, or I could say auto a equals vec1. And what auto will do is the square bracket operator for vector, the compiler knows it's going to be returning a float, so it just types it in there for me. Okay? So here, now what will happen is it'll actually print out the float, right? Because this says for whatever happens to be in the vector, it does type inference on that. Okay, someone just type inference the same time I say it. So it looks up what type it should be, infers it, and does it for you. All right? Now, be very careful about this because doing it this way will copy the thing in the vector. For a floating point or an integer, this doesn't matter that much because you're just copying an int. However, if this was a big long string, okay, or if this was a big data structure, this is copying that. So I'm not going to get into this now. I'm going to get into this more in the next lecture, but we can use a reference here, right? So we can use, okay, this is a reference, so we're just pointing to it, and so it'll produce the same result, but less copies. All right, so that was a bit hand-wavy. We'll talk about that next time. All right, what I want to do now is let's make our first class, okay? So I know I said that if you make classes, what you should do is you should put them in their own H file and then include the H file, but that's going to be a lot of work for me when I'm just doing it here. So let's just do it all in the one file, okay? So let's make a class called student. Class student. There, we've created a class. Tell me a language where you can make a class faster than that. People say C++ is hard. That's the easiest way to declare a class I've ever seen. Okay? So, in this class, we're going to have some public stuff and we're going to have some private stuff. So, let's say the public stuff is going to be down there. The private stuff is going to be up here. So, let's say we're going to have a standard string, first name. Okay, so I'm just going to say first. Standard string last. What else can a student have? Maybe they're going to have a student ID. Maybe that's going to be an integer, right? So int ID equals 0. We'll give it a default value. Okay, strings get default values on their own, but we can say, okay, maybe this is first and this is last, right? So we can give things default values within the declaration of the class, which old C++ couldn't do. Maybe also we have something like float average. So this is their grade average, right? So just something to say, okay, that's what it is. Now I'm gonna line all these up because I like doing that. I find it a bit more readable. So there we go. So there's our class definition. Nice use of whitespace, right? This is where the whitespace comes in. And even sometimes I'll do something like this, where I have the type, and then I'll do like this. I know some people don't like this. I like this in certain situations, not in other situations, because you can see all the types in one column, all the names in another column, all the variables, like all the default values in another column. Whitespace doesn't matter. It's just up to you how you prefer to look at things, okay? So those are the private things. Now, what's a function that we're going to need for this? Well, we're going to need a constructor, right? So a constructor, maybe the constructor is going to take in, let's just say that the constructor takes in everything. Actually, let's first give it a default constructor. So you like to give things a default constructor just to say, okay, if I ever construct a student with no arguments, what's going to happen? And in this case, nothing's going to happen because I've already got default stuff up here. So that is what's called a default constructor. And if I just say student S, that's what it's going to be. All right. So now let's make a slightly better constructor. Let's say we're going to pass in a string, which is the first name. We're going to pass in a string, which is the last name, and then an int ID and a float average. Okay, that all fits on my screen. That's excellent. All right. So what are we going to do down here? Well, let's actually use the initializer list right away. So I could type it all in the body of the constructor and then erase it, but in the interest of time, let's just use the initializer list. So our private member variable first, m_first, is going to get the same value that was in first. m_last is going to get the value that was in last. And the same thing for the integers. mid is going to get the value that was in id. And m_average is going to get the value that was in average. Sometimes I like doing this. Because whitespace doesn't matter. Lines it up a bit nicer. Just reducing that cognitive load, right? Sometimes you can't do that. It's okay. But that is our student constructor. We could have many different constructors in many different ways, but let's just leave it at that for now. And now, of course, we've got our data encapsulation up here and all that kind of stuff. Let's say we want to get the student's first name, right? So we would have, or let's say we want to get their average. So I would have a function. Int is what it's going to be returned. This is get average. It has no arguments to it. And what it's going to do is it's going to return the average. So if we ever want to get the student's average, we can have get average. We're going to have the same thing, get ID, return mid, right? We're going to have the same thing for standard string, let's say get first and return m first. I see a bunch of people out there saying hello in the chat. Hello. We are doing our intro class on C++, and I'm doing some live coding. Get last. And here is our last name. Return m last. So I see a bunch of people giving me tips. Trust me, we're on a journey here. We're going to get to all of those things. So what we have now is we have private member variables for all the data that you would want to have as a student, and then public functions to get all of those things. So let's make some students. All right. Let's make some students. All right. So here we are going to have student S1. And we are just going to use the default constructor for student S1. We're going to see what happens. Then I'm going to make student S2. That student is going to be Dave. His last name is going to be Churchill. His student ID is going to be 1 because I'm very old. And my average is going to be pi because I'm very dumb, right? And we'll make one more student, call this S3. This is going to be Jane Doe, who's going to have a student ID of 2022 00001. So Jane registered for classes this year, and their average is a 99.9 because Jane is a smarty pants. All right. So we've created some students. Let's compile now and see what happens. Now, it's very important to, you wouldn't want to write a whole program and then test it for the first time. You want to do a little bit of functionality, a little bit at a time. So now that we've written our class and we've written something to test the class, that's a good time to compile for the first time. All right, no compilation errors. That is very good. So what we could do is I could say here, standard cout s3 dot get last. Perfect. So what this should print out is S3 get last. That's the last name. So ideally, this is going to print out Doe. Perfect. Okay, so I've got a bunch of students. I've got their information in there. Now I can use it. However, it's going to get a bit tedious to print out all their stuff, right? One variable at a time. So what I'm going to do here is I'm going to make a void function. And that void function is not going to return anything because this is going to just be called print. And I'm just going to be printing out stuff. Okay, so what am I going to print here? Let's print all of the students' information. So I can say standard cout m first, then a space, then m last, and then a space, and then ID, and then a space. Actually, let me do this in a couple of lines so that it's not going off the side. MID and a space, and then M average. And then I will have a new line. Perfect. So now down here, instead of using standard cout, I can say s3.print. And here we go. Jane Doe, their student number, and their average. Okay, so that's, this is all standard first and second year stuff. I'm just showing you the C++ syntax for all of this. Perfect. Okay, so now let's say that I wanted to have, and this is going to be important in our course, okay? I'm going to have a const student. That means that I'm going to set up this student object and I never want that student object to change. Okay, so this looks fine. I set up a const student and then I print it out. When I go to compile this, I get an error. Okay, and it says passing const student as this arguments discards qualifiers. Now, what the hell does that mean? It means the following. I have a const student that I am calling a function on, okay? But that function could change the student, right? So I have a student that I want to be const, but I am calling a function on it. So what I have to do
is I have to declare this function as const. Okay? So once I declare this function as const, now it's fine. Because this means I have a function called print that will never, ever change the object. And if I try to change the object, so let's say in here I try and be sneaky, and I say m first equals Joe. So if I try and change the variables of the object from within a const object or a const function, oh my God, what happened, right? That's where C++ errors get kind of bad. So, but that whole thing basically just said, don't try and change the object from within a const function. So what that means is that if I wanted to, for example, call s3.getLast, which is just returning the last name, right? I can't call that on a const because these functions are not const. So what I have to do up here is call const. So each of these functions, where every single function I have on a class, where I am not changing the class, I should mark them as const, okay? That's just good practice. It is called const correctness. So anywhere you have a function that is not changing the internals of the class, declare it as const so that you can use that function on const member variables. It's called const correctness. It might seem a little bit anal, but it's what you want to do. Okay. Now, watch this. No, I think I'll get this into no, I'm getting into this next lecture. So really what you want to do here is be returning references to these things. I understand this is the first lecture of C++, so if you're out there saying that, oh, he's copying strings, blah, 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 I get into all of that in lecture number 2. Okay, this is all just for show. All right, let's do one more thing before we go, because I know I'm going long, but I'm just giving this for people who want the extra stuff. Let's make a course object, okay? Someone said, when would you ever want to make use of a constant instance of a class? Use constant variables or structs. Nope. A lot of the time you would want to make a const class. The canonical example of when you would want to make use of a const class is as follows. So let's say we want to say do machine learning. Okay. I'm jumping ahead of myself a little bit, but I want to show a good example of this. So let's say we want to do some machine learning with an object called data, and that data is really big. Okay, so this is my data. What I want to do is if I just pass in data, and again, I'm doing this in the next lecture, C and C++ are passed by value. So I would be copying this huge data structure here, right? So what I want to do is either pass it by a reference or by a pointer, right? Typically by a reference because it's a little bit safer. And then since that's a reference, I actually don't want this function to be able to change my data. I just want it to do the learning on the data, right? So I want to mark that as const so that I am 100% sure that this function will not change the input variable. Right? And so in this case, if I have a const reference to data and I call data.getValue, right? If getValue is not marked as const, then I won't be able to do that. So there are lots of examples of where we need to access const data, okay? Or const classes. And that will come up many, many times in this course, and I'll get back into that. All right. So enough of that. Let me get on with what I wanted to do for the rest of this course. Jeez. Okay. So let's make now we're going to make a class called course. What is that course going to have? Well, the course is going to have a standard string, and that is going to be the name of the course. We're just going to call it course by default so that it doesn't have a name. And we're also going to have a standard vector of student objects called M students. So that is going to be the context of our course. It's going to have a name, comp 4300. It's going to have a list of students in that. Okay. So for people asking out there that they didn't get that data example, tune into the next lecture and you will see it. Or look at the rest of the class when we want to, for example, draw a sprite. That sprite is going to be a class and we're not going to want to change it, so we're going to want it to be const. You'll have to trust me that there are countless examples of where that is useful. All right. So back to the last thing I want to do. So as public for the course, we're of course going to have a course private constructor, or sorry, a default constructor. And we're also going to have a course which takes a standard string name as a constructor, right? The course is going to have a name, and we are going to use an initializer list to say that the name of the course is going to get the value of name. Now, again, I know I should be passing these by references. We're going to talk about that in the next class. All right. But let's just talk about it now, okay? Strings are big things, okay? There are very few, if ever, any examples where this would be correct. Because again, what this would be doing in C++ is copying the string name into this constructor. So what we want to do is pass a reference to a string. We'll talk about references next time. And then because it's now a reference, we could actually change the name, which we don't want to happen. And so we want to pass a const reference to that, okay? So a lot of the time, whenever you're passing strings around in C++, you want to pass const references to strings and not strings themselves. So this is going to be more correct. Okie dokie. So what we're going to do now is we're going to have well, we want a way to add students to the class, right? So let's do a void add student. And then we will add a student S into the class. All right. And again, we don't want to copy this student. So for just now, I'm going to say we are going to be passing a const reference to a student, which you will understand in the next lecture. So I know that like people teach C++ in different ways. Some people would say, don't write something on the screen that they don't understand. You can drive a car before you know how a car works, right? So we're just going to write this for now. And then next class, we're going to explain what it means. And how would I add that? Well, I'm going to add that to my students vector by saying push back S. All right. So now that student will be added to my students vector. All right. How would I get my students? Well, I'm going to write a function that gets the students. Well, what am I going to be returning in that function? Standard vector student. So that's the return type of the function get students, which has no argument, which is const because we're not changing anything. Up here, add student is not const because we cannot add students. Right? Or sorry, we can't add anything if it was const. And since we want to add things, it's not const. This here is going to return the students array. Done. However, again, C++ is passed by value, so the return type would actually copy this big vector of students. So what we want to do again is return a reference to it. And since we don't want it to change, then this is going to be const. So this is one of the annoying things about C++ is that const can appear in 3 different places: at the beginning of a function, at the end of a function, and at the beginning of a variable. So this const means that this function will not change the class. This const means that whatever we're returning cannot be changed. That's what that means, okay? Const correctness is important, and we'll see why once we get into the course. All right, so now we've got a way to add students and we've got a way to get students. Now what we're going to do is let's make another print function. So let's say void print. This is going to be const because we don't want the class to change. We're just accessing values and printing them. And what we can do is let's use that range-based for loop. So for auto S in M students, So we know what that means now. It says use type inference. This is actually a student, right? So I could say for student s in students, but it's a good idea to use auto where we can. So for every student s in the students array, let's use the print function of the students. And I guess I should, let's go const auto s so that it's not going to be changed. For every student in the vector, let's print it out. All right, let's see. Do I compile? I do not compile. Oh, because I had this example here somewhere. Where do I have that? Probably down here. We'll find it in a second. Oh yeah, so this doesn't work anymore. All right, so now what I want to do. Someone said it looks like I can paste const anywhere. I know. So people out there are asking what the ampersand is. That is called a reference. And I am very briefly explaining it here, but I am going to explain it in excruciating detail in the next lecture. So please tune in to lecture 3, which is the second part of C++. We'll be talking about pointers and references in memory. Okay. All right. So let's create a course. So now I have a course. Let's call that course comp 4300. We're going to have a name, which is comp 4300. And what I'm going to do is say comp 4300.add student, and that's going to be student S1. And then I can copy and paste this, and I'm going to add student S2, student S3, and watch this. I can actually do this as well. .add student, and then let me make a new student here. And this student is Billy. Their last name is Bob. Their student name is 3, or their student ID is 3, and their average is 50. Boom. All right. Now down here, comp4300.print. Hopefully this works. Oh, I've got an error. Okay. So I've got mstudent.pushback_s. Okay, so it says mstudent was not declared in this scope. That is on line 68. So let's look at line 68. I can type this, go to line 68. Oh, that's supposed to be mstudents. So you all failed. You were supposed to catch that error. I did that on purpose, right? Okay, let's try and compile again. Okay, again, we've got mstudent on line 63. So here we go. Oh, there we go. And it worked. So we created some student objects. We added some student objects to our course object. And now we have this functional system in C++ in just a few lines of code. Like, could you reasonably write that in any other programming language as quickly? I mean, you couldn't do it faster, probably. All right, so let's do something interesting. For the last thing I want to do in this course is I want to show you file input, okay? Because we're going to be using that a lot in this course, so you can use that. I want to add a function to my course which loads student information from file, okay? I would recommend students in the class to not take a lot of advice from chat because sometimes it's right and sometimes it's wrong. I will eventually get to it. All right. So let's make this function load from file. We're going to have a standard string file name, and this function is not const because we are going to be loading the class from a file. Okay? So in order to do this, the first thing we're going to need to do is we're going to need to include the tools to let us work with a file. And that is the file stream tools. All right. So let's do that. Sorry, I just have to close this notification over here. All righty. The second thing I'm going to want to do is I'm going to want to have a list of students in the class. I've already made one of those. So if I just cat students.text, here we go. So I've got a bunch of students in the same format in this file that I've already written. All right. So first name, last name, student ID, average. And then we go to the next line and we do student, last name, ID, average. And you might say, oh my God, I've heard of file reading in C and C++. It's so annoying. It's so verbose. Just watch. Just you watch. I will challenge anyone to do what I'm about to do in any other programming language in fewer lines of code. Okay? Without writing libraries and then calling that, So that is my student data. It's in a file called students.txt, and that is what I am going to read. So down here, what I'm going to have in my main function, instead of declaring all these students, is I'm going to have, all right, so I'm going to have my course. I'm going to call that course C. That is going to be comp 4300. And then I'm going to c.load from file. And that's going to be students.txt. All right, let's compile and run. Okay, there's no compiler errors, but it doesn't do anything because our load from file thing doesn't happen yet, right? Oh, now, sorry, actually I didn't print. So c.print, that's going to print all the students in the course. And again, we haven't actually loaded anything yet, so it won't print anything. But we know our printing function works because we tested it before, right? All right, so how will we load from file? Well, it turns out that in order to load something from a file, we need a file input stream. So streams in C++ are so nice. They do things for us really, really easily. So watch this. Standard, because the input file stream class is within the namespace standard. It's an IF stream, which stands for input file stream. I'm going to call this variable fin for file in, and then the constructor, I give it the file name. Bam. Look at that. That's crazy. Now watch this. While, okay, sorry. Let's say I want to read all of the string tokens from a file. How would I, oh, sorry, someone pointed that out. Someone's paying attention. Great job. So let's say I want to load in all of the different string tokens from a file and just print them to the screen. Sorry. So what I can do, I'm going to have a standard string. I'm going to call this temp, okay? So this is my temporary variable that I'm going to read things into. And I'm going to say while fin temp. So remember when we had standard cout? So standard cout was the opposite direction. We are using a stream, right? So this string is getting sent into standard cout. If we do the opposite thing, we can read data, even from files. So fin is going to send its next string token into temp. Watch this. And if there are no more tokens, this loop will no longer run and it will exit. So let's say while fin to temp, standard cout temp, and then a new line. So it's just going through the file, reading everything, and printing it out. Look at that. So every individual token, so some people are asking, what is a token? Tokens can mean different things, but essentially a token is a string that is separated by some white space or by new lines. Okay? So in C++, I can get the next token by just using this operator. This just says, get the next string that's not white space and it's not a new line character, and put it into temp for me. Super crazy cool. All right. Now, I'm going to need some things in order to read in the first name, the last name, the ID, and the grade of a student, right? So let's say instead of temp, I have the first name and the last name. So I've got two strings now. One is called first, one is called last. And then I'm going to have an int called ID, and I'm going to have a float called average. So now what happens is I can say while, so what is my while loop here? Well, the first name is the first thing on a line, right? So I can say, while I have a valid first name as the next token, what I can do is, okay, now my first name is stored in first, all right? I can say fin, so read the next token, which is the last name, into last. Read the next token into ID. The next token will automatically be converted into an integer for me. It's crazy how cool that is, right? So like the C++ file reading stream will automatically convert it into an int. Now, if it's not an int, it'll throw an error. And then the last one will send it to the float, or sorry, not to float, to average. So on each line, it says, while I have a valid first line character, read in the first name, then read in the last name, read in the ID, read in the average. That's pretty quick. But not only that, remember when we had standard cout, hello, and then we can give it another thing, and then we can give it another thing like this. We can do the same thing with the input version. So I can say fin, sorry, fixing my white space, fin last, ID average. So this literally reads in everything for me. And if this is true, now I can create my student object, right? So let me create it in place. So I'm already in my course class because it's been a while. Let's look at that. We're inside our course class. So what do I want to do with this information now that I have it? Well, I want to add student. Add student. And now I've successfully read everything in. So I can just read in first. I need to construct the student. First, last, ID, average. That's it. This is the entire function that loads all of those students from the file, stops at the end of the file, converts everything to integers and floats. Show me another programming language that could do that easy. Seriously. Right? People make fun of C++, but there it is. I loaded all of that information from the file, stored it in the student class, and then printed it out. Someone said Python. I challenge you to write that in fewer lines of code in Python. Just go do it. Go do it. You will not be able to, like, you'd probably do it in the exact same amount of lines, right? But not fewer. All right. So, here we go. We have created a course, loaded the data from a file, printed that data out. In this course, every single game that we make is going to have a configuration file in which, if I load that, so the configuration file for all of our games in this course are going to look something like this. And so you've got to write the code to be able to parse in that stuff. And so what you're going to do is you're going to write code kind of like this. All right, where you say, okay, I'm going to parse something in, and I'm going to do something with that. So feel free to just copy and paste this and use that for your classwork. All right, C++ memory. We're going to need to know a little bit about memory for this course because, again, in C++, you have to manage your own memory. So there are two different types of memory in C++, stack memory and heap memory. Stack memory and heap memory have different properties, and you use those types of memory in slightly different ways with a little bit of different syntax, and we'll get into that throughout the course or throughout the lecture. When a program is launched, the operating system gives it access to a number of areas in memory. And the main two that we can manipulate are the stack memory and the heap memory, as I mentioned up here. Both the stack and the heap are stored in RAM, so you're still going to use both of those types of memory in the sort of the same way. They're still in RAM. The difference is determined by the operating system when the program runs, and so where they are in memory is going to be different.
So what are stack and heap memory? Well, at a basic level, they both just store data, right? That's where our variables live. That's where our data lives. And so in order to use the stack or heap memory, just like any other programming language, we're going to request some amount of memory from either the stack or the heap, and then it gives it to us, right? So even if you've used another programming language like Python or Java, you're still requesting memory. You don't always have enough memory. Like I could request a terabyte of memory and I wouldn't get it. Or I could request a megabyte of memory, or maybe just 4 bytes for an integer or something like that. So we're going to request an amount of memory via, say, if I say int I equals 6, that is me requesting an amount of stack memory to store an integer. So the main differences between the stack and the heap are the size of the memory available. So it turns out the heap has a lot more memory. The way that the memory is found and allocated. The speed of the memory allocation. Turns out the stack is way faster to use in general. The way that we request memory in our code, so the syntax is going to be a little bit different. And stack memory, this is very important, stack memory is automatically deallocated when it leaves scope. And we'll have an example of that and how that's going to impact the way that we design our code, etc. So here's some examples. Here's an example main program. If we just say int value equals 5, that is a stack allocation. So by default, if you haven't specified, I want to use the heap for this, then you're going to be using the stack. And so this integer here is allocated locally on the stack. Int star hval equals new int. That is how we allocate memory on the heap. And so if I want to access this memory and then set that to something, I would have to dereference that pointer. We're going to get into pointers later, okay? So we're going to get into pointers, but just realize that there's a bit of a different syntax here. So that's what this means here. This is just talking about syntax, and I'll get into the details of this later and exactly what this means. Similarly, we could have stack or heap allocated arrays as well. So instead of having just a single array here, I could have a stack allocated array of size 5, and I would say int a 5, and that would be allocated on the stack. And then if I wanted to do the same thing, but on the heap, what I could do is say int star heap array, this is just my variable name, equals new int 5. And then I could set or get values from that array just like a stack allocated array. But again, we're not going into too many details here. This is just an example syntax to show you that yes, we do have to use this new keyword in order to get heap allocated memory. Now it turns out that at the end of the lecture, we're going to get into something called RAII, and we're not actually going to have to type new because we'll do something that takes care of all of that for us. Okay. So so that was an example of a simple primitive type variable and an array, but now here is a class that I've created. So a custom class, my class C, maybe I have some arguments to that class, that is allocated on the stack. Versus if I want to heap allocate a new class that I've created, then I would say my class star, so again, we have to use a pointer, equals new my class. So this is just saying that by default, if I don't specify new, that's allocated on the stack. If I do specify new with a pointer, then that's allocated on the heap, okay? So I keep saying stack, heap, stack, heap. What is the actual difference between them? So stack memory, first and foremost, the most important thing about stack memory is that it has a predefined size. Someone says, what is the stack frame that's available to us? So the amount of memory available to us on the stack is usually pretty small, on the order of just a few megabytes, okay? So we want to store as little as possible on the stack, but at the same time, that's because it's very easy to run out of stack memory. So for example, if you've ever used the website Stack Overflow, this is what a stack overflow is. Our stack memory is very, very limited, and it's very easy to run out of stack memory. So if I do something like allocate a gigantic array on the stack, or if I have like an infinite recursion that puts a bunch of call pointers on the stack to functions, then that is a stack overflow. Our stack has run out of memory. Local variables without the new are allocated on the stack by default. So if we don't say new, we get a stack allocated variable by default. Also, something that's stored on the stack, if you're familiar with like assembly programming, now this will not come into play in our course. We're not a security course, so you can sort of operate without this knowledge, but it's nice to know that program function calls and return addresses are also allocated on the stack. Okay, so when you like call another function, the reason it knows how to go back to a piece of code after it's finished running is because its variable is pushed onto the stack. Okie doke. So stack memory is, because of that, because it's predefined size, it's also known as static memory, meaning that the amount of memory, it's for two reasons. The amount of memory that you have on the stack is static, and you can't do any what we're going to call dynamic memory allocations, okay? So anything that you put on the stack, the memory size of that needs to be known at compile time. So that means that any memory allocation that we need to do that depends on runtime variables or dynamic memory sizing must be heap allocated. So for example, if we want to get some data from the user and we don't know how many inputs there are going to be, then that's something, compile tile, thank you, compile time. Let me fix that now so it's done on the when I release the slides. Thank you very much. There is no compile tile. But what this does mean is that because the stack memory has to be known at compile time, if we say, for example, to the user, input some number of names, right? We don't know how many names they're going to input, so the data structure that we have to use to store those is going to have to be allocated on the heap. And I apologize again, but the kittens are back and they are very, very loud. I'm not sure if you can hear them or not, but give me 1 minute and I'll be right back. Okay. This is what happens when you try to do it live, right? And you have kittens in the house that you want to show off. Sometimes they don't always cooperate, but they're so cute. They were just like pawing at the door because they can see me through this door because there's windows and stuff. So they're just so cute though. All right. So what does this all mean? Let's have a look and do an illustrated example. So let's pretend over here that we have our stack memory, right? And the way that I'm going to lay this out is that this memory is laid out not like, this is not exactly 1 byte or not exactly 4 bytes. This is like, maybe we'll have an integer per stack element, okay? And you'll see what I mean in a second. We're going to walk through this example and show how the memory is allocated and then deallocated when it goes onto the stack. Okay. So we've got int main, we're going to set up some data structures here on the stack. So first thing we're going to do is, and I've got a little arrow over here indicating the current line of code that's being executed. So this line of code has just been executed. So we say int I equals 6. Since we have no new on this line, then that variable I is going to be stack allocated. Okay, so over here on the stack, we see that we have a number 6 that's gone onto the stack. All right. Then we're going to allocate b. So int b equals 10, and we see over here the stack memory, we have a 10 that goes right on top of the 6. You're all, by now you should know the difference between a stack and a queue, and the reason it's called stack memory is because it's literally a stack, okay? So we're going to build on top of it, and then it's going to deallocate in the reverse order. Then maybe I have some point data structure, which stores an x and a y. And we see here we're going to construct a point with our x and y, and then the data for that point structure is going to be pushed onto the stack here. Okay? Now, internally, the compiler, whenever you reference the variable I, it knows where on the stack that variable lives. And so like we don't put the variable name over in the stack or anything like that. It's just the compiler knows when I say I mean this memory location. When I say B, I mean this memory location. So it sort of takes care of that for you in the background. So what happens now is that we are inside this local scope. So this block of code. Now it just happens to be main, but the same thing would happen if we were in any function or any block of code. So when we reach the end of a block of code, what's going to happen is all stack allocated variables are going to be deallocated in the reverse order that they were allocated, okay? So the most recent thing that we allocated is going to be the first thing to be deallocated. So what happens is first, this point, the 5, 4, that is going to be deallocated. Then B is going to be deallocated, and then I is going to be deallocated. So what happens when stack memory is deallocated? If it's a primitive data structure, then it just gets removed from the stack. But the very cool thing is that when a stack allocated class, so this is a custom class that we've written, when a stack allocated class is deallocated, when it runs out of scope, then the destructor of that class is called. And that's going to let us do a lot of cool things later. And after I finish the PowerPoint slides, we're going to have a live coding session where we abuse that. Someone asked a question, are the variables also stored using stack inside stack frame? I'm not sure exactly what that means. I can't interpret that question, so I'm just going to pass it for now. But just realize that locally, like without the new keyword, it's allocated on the stack. That's the thing that you need to understand right now. So that was stack memory. It's actually pretty simple. Stack memory is really easy. It grows up and then it gets deallocated down. Heap memory. Someone asked another question. Are they stored contiguously in the stack? Yes, with some caveats. For the most part, yes. So if you allocate I and then you allocate B, 99% of the time, they will be contiguously allocated in the stack. Okay, so it just goes right on top of the last thing that you allocated on the stack. And I will actually show you, I'll prove that to you when we do the live coding session. All right, so heap memory. There is much more space available on the heap than on the stack. So that's why heap memory exists. Heap memory is allocated via the new keyword. And the way we allocate heap memory is if we have some type, we have to say type star, meaning a pointer to type, var name, so that's our variable name, equals new type, right? And so it would be int star I equals new int, for example. That's how we would allocate something with new. And the syntax, so this is a little bit differently than how you would do it in C, but essentially what happens, and essentially, right, there's more stuff going on, but when you call this new keyword, essentially, C++ is calling the malloc or memory allocation function underneath the hood. Then what happens is the operating system goes out to find a contiguous chunk of memory from the heap and then returns a pointer to it. Okay? This turns out to be actually very complicated and very expensive. And I have a diagram that shows that later, but we're going to try and use the heap as infrequently as possible. So we're only going to use the heap when we need something that's dynamically allocated or when we have a ton of data that we need to store. And then once the operating system finds a contiguous chunk of memory, it's going to return to you the pointer that you can then access that memory, okay? So for now, just realize that literally all that a pointer is an address. It's a memory address, okay? So up here, type star variable name, literally all that is a memory address with a type associated to it. So it says var name stores an, like it's going to be an actual unsigned integer that represents a memory address somewhere in the heap. And that, well, it could be also in the stack. That memory address, we know, points to a specific type. So if we have an int star I, then I is a memory address that points to an integer. It's just a memory address and nothing more. So here's my example for showing how the stack and the heap are going to interact, okay? So over here, again, I have a stack. This is going to work in the same way that our last example did. But over here, I also have a heap, okay? And I've just given the heap some memory addresses so we can keep track of pointers. Now, over here, we don't have memory addresses next to the stack, but just realize that, yes, the stack does have, like, all of these locations in memory still have addresses, but I'm not including them here because it'll muddy up the example a little bit. So I've just given like dummy addresses to the heap, and inside C++, when you're looking at memory addresses, they're recorded in hex. And so that's like OX whatever. So this is the first memory address, the second one, the third one, the fourth one. In reality, these will be 64-bit integers, 64-bit unsigned integers, these right here. But we just want a simple example, right? So let's just cut off all the leading zeros. And so this is the first one, this is the second one, this is the third one. All right. So what's going to happen when we run this code? The first thing we're going to do is we're going to allocate I, right? So int I equals 6. You look, there's no new, and so that is a stack allocated variable. So over here, we have 6 that goes onto the stack. Next, we're going to allocate j. That gets 10. There's no new, so that gets allocated onto the stack. Now, here's where things get not complicated, but just pay attention, right? So two things are happening right here. The first thing that's happening is actually a little bit hidden if you hadn't thought about it before. So this, it says new, right? So you think new, okay, we're going to allocate this point, and PT just means point. I just couldn't fit the whole word point all over here. So we're going to ask, give me a pointer to a point called P, and allocate that on the heap. So the first thing that happens is that point gets allocated on the heap, okay? But there's also something that gets put on the stack. The pointer itself gets put on the stack, okay? So just watch. This is what happens. So we execute this line of code. The new point has a 5 and a 4. So the heap is going to grow down. That's just how it works in memory. So we have a 5 and a 4, so that's our point that lives on the heap because we said new. But back on the stack, the address of that point gets put onto the stack, okay? So this P variable is on the stack, but the data that it points to is on the heap. See how that works? Okay, so let's explain that one more time because it's not super intuitive at first. So we said that anything that gets allocated with new gets put onto the heap, and that's true. So we said we ran this line, that this data, the 5 and the 4, gets put onto the heap. But we also have this variable P which stores the pointer to that data, and that pointer lives on the stack. Okay, there we go. Now, the next thing we're going to do is we're going to have a stack allocated array. And we can just say int r2 equals 3, 4. Okie doke. Now, and then we have 3, 4 that grows upwards like that. Now what happens is the exact same thing that happened last time. Okay? So, we've reached the end of the scope in which these variables were declared. And so if any locally declared variable was in this scope, it's going to start now be deallocated in reverse order. So here's what happens. The array was the last thing that we allocated. So that gets popped off the stack because that is a static array of primitive data types. So that just gets cleared off of the stack. Next, we have our pointer. Okay, that is on the stack. That gets cleared. Just give me a second. Next, the j gets popped off the stack, and then the I gets popped off the stack. But look what happened. Even though the stack allocated variable P got popped off the stack, the memory that it had allocated is still on the heap. Okay? So the pointer got deallocated, but that didn't do anything to the heap memory. It's still living there. Okay, so this is why raw pointers are unsafe, because you can, well, there's a number of different reasons why they're unsafe. One of the reasons that people used to hate C++ is because of stuff like this. This is not automatically garbage collected for you. So what you have to do with pointers, when you allocate something on the heap manually like this, you also have to remove it from the heap manually. So in order to get something off of the heap, we would have to do this. So before we get rid of this pointer, before the end of the scope of this function, we would have to say delete p. So that's the manual removal of the memory from the heap. Okay? So you can see how this is going to get very annoying. If we want to use heap memory, which it turns out we do, we're going to have to allocate it using new and then delete it using delete. And this is the first real example that we've run into so far where that's a little bit annoying. We didn't have to do that in other languages, right? So toward the end of this lecture and in the live coding section, I'll show you that yes, that is annoying, but there is something really cool that we can do so that we never actually have to do that in practice, okay? Now, this process, I told you that heap allocation was a little bit intense. This is a diagram of what malloc does under the hood. Okay, so up here in the top left, this flowchart is the logic of malloc. Now, I'm not going to go into the details of it, but it has to, like, it's operating system specific. It has to talk to your system. It has to say, okay, I want exactly 1,300 bytes. Well, find me 1,300 bytes of contiguous memory, right? It's quite complicated. It's slow. It is slow to call malloc. Free. So free is what's called when you actually use the delete keyword. So even just freeing the memory is also kind of complicated. And this is realloc, which is a reallocation. We're not going to get into that. The whole point of this slide is not to memorize the details. It's just to show you that whenever I do something on the stack, it just says, oh, what's my current stack pointer? Put it at the next one. Done. Versus a new allocation is all of this, okay? So that's why the stack and the heap are so much different in the speed of allocation. Now, the speed of actually referencing the memory, like getting memory, is the same. And we'll get into cache coherency and stuff way later in the course. But just realize that stack allocation is way, way faster, and so we want to use that wherever possible. Okay, so I've given a simplified version of the C++ memory layout here. It's actually quite complicated, and it's also specific to the operating system and a little bit specific to the compiler. A lot of the details of that don't matter in this course. This is like, depending on whether it's an executable on Windows or a binary on Linux or Mac, like there's all this stuff that lives on the stack that's just like, okay, we don't ever need to know that for 99% of programming. Now, if you get into like systems level stuff, of course you need to know that sort of thing, but not for game programming, okay? Just remember, stack is fast but limited, heap is slow but large. And also a small detail, if you get into this sort of thing, is that for memory addresses, the stack grows upwards. Oh, is it stack grow downward? Heap grow upwards. One of them, when you allocate more things, it goes down. One of them, when you allocate more things, the pointer goes up. It's such a minor detail that you don't need to know, but it's a bit strange that one goes up and one goes down. All right, so now we've talked about stack versus heap, but it's very, very important that you really know what a pointer is. I just kind of showed what a pointer was, but you're going to need to know what a pointer is if you're using C++. All right. A pointer in C++ is the exact same thing as a pointer in C, okay? It has a couple of more use cases in C++, but the syntax and stuff is exactly the same as in C. And again, a pointer stores a memory address. That's it. If anyone in any class ever asks you what a pointer is a memory address with an associated type. That's it. Okay. And I know that like what you can do with pointers and the syntax of pointers and keeping that all in your head can get super complicated and super frustrating, and it can be dangerous to use. But at the very, very base level, a pointer is a memory address with an associated type. So if you want a real world example, a pointer is the address of my house. That's it. So I'm not going to tell you what that is, but a pointer is just an address, right? Now, a pointer also might store, this address is where Dave lives, right? This address is where Jane lives, right? This address is where Bill Gates lives. So you've got an address and you've got a type. That's it. That's what a pointer is. There are two important things that you have to realize when it comes to pointers. There's the pointer variable itself, and then there's the thing that the pointer points to, right? So just remember, the pointer variable is just a memory address, and then that memory address points to some data somewhere, okay? So if you modify the pointer variable, you're modifying the address that it points to. To modify the value of the data in memory that it points to, you have to dereference it, okay? So if we take the house address as an example, if I write down my address and I give it to you and I say Dave's house, my address, okay? If you modify the address, that's all that happens. So if I was living at like 101 Main Street and you wanted to change the thing in my house, well, modifying the address doesn't change anything in my actual house, right? My house is the data on the heap. So in order to modify the things in my house, you have to travel to my house. And the C++ equivalent of that is dereferencing it, okay? So you have an address, and then you have something in memory that it points to. And in order to get to the thing, in order to go to the house, you have to dereference it, all right? That's it. All right. And raw pointers, I'm going to say raw pointers because we'll talk a little bit about smart pointers in this course. Raw pointers can be very unsafe. And the reason for that is because raw pointers basically allow you to modify anything at any time. And that's quite dangerous, okay? And I might give an example of this when we're live coding, but let's just see. Okay, so pointers are just memory addresses. The canonical example of using pointers is to get data on the heap, and then we get an address that points to that. But you can also point to anything, even data on the stack, okay? So watch how this works. So we've got our stack over here again. And this time I have actually given addresses to the stack, just so we can show this example. So the first thing we're going to do is we say int I equals this, 6. This is a local int variable. So that value of 6 goes onto the stack. Now, here we have int star p. And that's all that we've said. So what this says, I'm going to create a pointer to an integer. Okay? Now, if we don't give this a value right away, then what actually lives on the stack here is undefined. So whenever you allocate an integer or a pointer in C++ or in C, and you do not give it a value right away, then it is undefined, meaning that the value of this is not determined by the compiler. It is actually whatever happens to be in memory at that location. So whatever random bytes were here before, that is what's here now. So this is very dangerous. You pretty much always want to give a default value. So for example, if I had said int I without giving it a value, in other programming languages, that might get a value of 0, but not in C++. It would just be whatever random data is currently living in memory there, okay? So I know this is bad practice, but I just wanted to give you that as an example here. So now we have a pointer to an integer. So here is the syntax of C++ pointers. There are two things that we can do with pointers. The first is we can set it to the address of something, right? So if I actually want to give P the address of the variable I, because remember, P is just storing an address to an integer. That's it. Storing an address to my house. It's just writing down an address. So I'm going to say I want P to be equal to the address of I. And so I is what we call a unary operator. So it operates on a single variable, unlike plus, which is a binary operator, operates on two things. And it says if we put, in C++, if we put the ampersand, or the and, in front of a variable, then that is going to get us the address of that variable. So what happens is, once we execute that line of code, P is going to be assigned the address of I. So the address of I was 0x1, and so the value that gets put into P, which lives on the stack, is 0x1. See how that works? It's just an address, and all it does is it points here. Okay. And then if we actually want to modify not the pointer, but the data that the pointer points to, which would be the value of I, right? Then we dereference the pointer. So if we put, and this is where pointers get a little bit complicated for some people, because if I say int star p, that star means, okay, I'm declaring a pointer to an integer. But if I down here use the operator star in front of a variable, it means dereference that variable. So it says, this basically says, get me to the data that lives at the address that P points to, and then set the value there equal to 7, okay? So P over here says 0x1, so dereferencing that is going to give us the variable that lives here at 0x1, and it's going to set that value equal to 7, okay? Now, I know that this is confusing, and I really wish that when they did C and C++, they had just used different, like, why not use, I don't know, the @ symbol for this? It would be perfect. It would literally be perfect if they had used the @ symbol for dereferencing, because it literally says at the pointer. Why? Why, C++, didn't you use the @ symbol? This kind of makes sense, I guess. It's like a pointer. It looks pointy. But if they had just used the @ symbol here, it would have been so perfect. So I'm going to apologize on behalf of C++ to new students, because this star, right, Shift 8, I had to look at the keyboard for that. That's really sad. Shift 8, like, that is used for creating a pointer, dereferencing a pointer, and also multiplication, right? So it's annoying. But just realize that that's what it does. If it's in front of a variable like this, it's a dereference. If it's after a type like this, you're creating a pointer to that type. All right, let us do a, what's going on here? Let us do another example. So here, I've already stepped through what happened here. So let me go through this quickly. We say int star array. Oh, this is C++ arrays and pointers. I did not do the step through on this. Why didn't I do that? 1 second, I apologize. Okay, so C++ arrays are basically just pointers to locations in memory. Okay, so dynamic arrays, at least. So if I want to have a dynamically allocated array in C++, now just realize, okay, in our course, we're not actually going to be doing any of this. You should just know what it does. We're going to have really nice code. Again, at the end of the lecture, we're going to show how we're going to avoid having to do any of this manual pointer nonsense. It's very powerful when you need it, but we're going to get around the need for it. So if you don't fully understand it, you're still okay for this course. But please, I would load up a terminal and start programming and get used to it. If we want a dynamically allocated array, here's what we would do. We say int star array. Now, int star array, that's just a pointer to an integer. That's all that it is, right? So it's going to be a pointer to some address in memory. That's what an array is. But in order to allocate the space for, say, 3 integers, we have to say new int bracket 3
bracket. So this is how we would allocate an array with 3 integers inside it. Now, if we want to give them some values, okay, because as of right now, when we run this line of code, there's nothing in that array. It's just random data. So if we want to access variables in the array, we would just say like array 0 equals 5, array 1 equals 2. And now let's do some math, okay? Let's say that we want to get access to the third element of the array. So 0, 1, 2. So the 2th element of the array, if you will. So we could say array 2 equals 20. We could do that. But what we can also do is the following. We can do some pointer math. Now, again, if you don't fully grasp what's on this slide, it's fine. Try and understand it, but we're not going to be doing anything this crazy in the actual course itself. I just wanted to show you how fun C++ can be. So instead of saying array 2 equals 20, we're going to add 2 to the array pointer. So here, the pointer points to 0x1. We're going to add 2 to that to get 0x2, and then dereference it, which means get me the thing that lives at 0x3, and then set that value equal to 20. So it turns out that in C++ and in C, the following syntaxes are equivalent. If I say array n, that is equivalent to the statement add n to the variable array and then dereference it. This is just shorthand. It doesn't even have to exist, okay? But the funny thing is, look at this, array plus n. Because array plus n is just adding 2 integers together, a memory address and a number, I could actually swap these around. And so n plus array is the same as array plus n. That means in C++, instead of going variable name bracket number or index, I can actually say index bracket variable name. And the reason for that is because n and array are just integers, right? They're pointers to some memory. And if I just say array plus n, then array plus n. So what's array? Array is a memory address. It's a pointer, right? So a pointer plus some value, right? So say that was 2 over here. So the pointer plus 2 is going to be 0x3. And 0x3 is equivalent to, well, the address of the second or the 2th thing in this array. Okay? So pointers are just memory addresses. You can add to them, you can subtract from them. And under the hood, when you index arrays by the bracket operator, all you're doing is adding this number to this number and then dereferencing it. All right. Someone asked, why did we start with a pointer instead of a regular array? Because I'm just showing you the syntax of C++ arrays or pointers, but of course, as you have alluded to, you don't want to say regular array. This is a stack allocated array or a static array, okay? So the difference being that this value here, the size of the dynamic array, meaning, it's heap allocated, that could be 3, or it could be read in from some variable or read in from a file. This can be dynamically allocated, but this one, static arrays, their value, their size has to be known at compile time. Okay, and we can do the exact same thing that we can do with a stack allocated or static array that we can do with a heap allocated array. So we can do the exact same thing. All right, so pointers. Why do they exist? Why do we have pointers? There are several reasons to use pointers in C++. These are in just like an order in which I thought of, okay? So in C++, we must use pointers whenever we want to use inheritance, okay? So in C++, if we have a base class and we have a derived class, if I want to set up a base class variable which points to a derived class, now this is a 4th year computer science course, I'm assuming you all know about inheritance, okay? So in C++, if you if you want to use inheritance base class pointing to a derived class, you have to use a pointer. Now you can also use a reference. Okay, you don't have to use a pointer. You can use a reference if you want to. We'll talk about references in a bit. Now, also, there's pass by value versus pass by reference. And I'll give you an example of this. Okay, so we'll do an example of that in the near future. And also pointing to large data. Since large data can't live on the stack, we need to get it heap allocated. And in order for us to talk to the heap to say, hey, do something with the data, we need to get that pointer to the heap data. Okay, so these are the three main reasons why you would want to use pointers. There are more. I'm not going into them. This is 99.9% of real world use cases of using pointers in C++. So C++ references are essentially, if you've heard of a reference, in C++ we have pointers and we have references. References are essentially safe pointers. Okay, so pointers are very unsafe, and C++ decided to say, we're going to have something which is a safe pointer, and that is a reference. So the syntax with a reference changes a little bit, but we're going to see how that works. So to use a reference, which is essentially a pointer, but a safer version of a pointer, instead of using star, we're going to use ampersand. Okay, now again, ampersand is, why did they use ampersand? Because ampersand is used in other places. It was like they didn't have enough memory to use 5 different characters, you know? So a reference, the reason we call reference a safe pointer is that a reference must point to existing data. We can never have a reference, okay, never. In normal operation, we cannot have a reference that points to nothing or points to null, okay? And that makes them almost always safe. Now, of course, if you know enough C++, you can come up with examples where references don't point to anything, but for the most part, and especially in this course, a reference will always point to something. So, it is generally advised to prefer using references to pointers wherever possible in your code, okay? So, all of the same reasons to use pointers, we also want to use references, but we would prefer to use references wherever possible. Let's look at some examples, because I know that I only learn through examples. And again, we're going to do examples of this in the live coding session later as well. So pass by value or pass by reference. By default, C++ passes all variables by value, okay? All variables are passed by value. And pass by value has a cost for copying large amounts of data. Okay? If your data structure is large, then you do not want to pass it by value. Also, not only do we want to copy it because it could be large, maybe we want to be able to modify the value that we passed into a function, right? So we can use pointers to accomplish pass by reference, but ideally we would want to use references for it. So let's look at an example of pass by value versus pass by reference. All right. So I'm going to have a function here, and this function I'm just going to call tenify. All right. So the reason it's called tenify is because you take in an integer value, it's just called a, and we're going to turn a equal to 10. All right. So we're just going to set a equal to 10, and then that's it. It's a void function, doesn't return anything. It just says a equals 10. So down here in my main function, if I say int I equals 12, and then I call tenify on I, what is going to be printed out? Anyone out there in the chat want to say what's printed out by this function and why? All right. Got an answer, got a correct answer, and an incorrect answer. So just watch this. Pass by value is the default behavior in C and C++. That means that when we pass in I, we are passing a copy of I. Okay? So the number 12 gets passed in here, but this int a variable, that is local to this function. And the value of I outside of this function does not get changed. Okay? So think of it like this. If I have a piece of paper and I write a number on it, and there's a person over there who their job is to change the number to the number 10. Okay? So they're the 10ify function. I have a piece of paper with the number 10 on, or with the number 12 on it. So my variable, I'm going to have 12 on that function, or on that piece of paper. So pass by value means I'm going to copy it before I give it to that person. So when I copy it, I get a new piece of paper. I write down the number 12 because that was what was on my piece of paper. That person takes the copy and then changes that 12 to a 10. And then what happens is they don't do anything with that. They just keep it there. Then I print out what's on my piece of paper, which is still 12, because I gave that person a copy. So I pass this a copy of I, not the actual I. So that's weird, right? Why would we have this function if it doesn't actually do anything, right? Because it's modifying a copy and then returning. Well, what we actually probably want to do here is called pass by reference, which means that we want this initial I to be modified after we finish this 10ify function. So we can do that in two ways. The first way is to pass a pointer into this function, right? So again, we're passing a pointer in, right? Okay, so what does this do? Well, we say int I equals 12, so now we have that I that lives on the stack, right? So I lives on the stack, there's a 12 over on the stack. And then we say 10ify the address of I, okay? So C++ is still passed by value. So what we do is we pass in a copy of the address. Okay, so now what I've done is I've written on the piece of paper my address. Now I copy the address, pass the address to the function. Now the function's going to go to my house and change my house to a 10. Okay, so it gets passed in an address and it says look up, dereference that address. Look up the memory that this address points to, and this address points to where I lives, and change that to a 10. So if we print this out here, this is going to be 10. This is going to print a 10 because we modified what lived at the address of I. And then, so that gets changed in memory. All right. Be careful whenever you pass a pointer into a function. If that pointer points to either A, nothing, so, if the address of the pointer is 0, meaning it's a null pointer, and you try and dereference a null pointer, as Brett the Hitman Hart famously said, you're trying to dereference a null pointer, you're going to crash. Your program will just crash. So be careful of that. Also, if this address happens to be something that your program has not been given access to by the operating system, your program is going to crash. Okay? Also, if the thing it points to, if it is valid memory, but it doesn't point to an integer, then this is going to assume it's an integer and cast whatever it is to an integer. So there's lots of ways that this can be unsafe. Okay? Here's the preferred way to do this. Passing a reference. All right. So the cool thing about references is they get rid of the dereference operator and they get rid of the address of operator. So it's much easier to use a reference, okay? So down here, this is the reference version of this same thing. So we're going to allocate 12, and then we're going to 10ify I, but let's see what happens. So up in the 10ify function, now we're going to pass in a reference to a number. So a reference is still an address of something, okay? But it's a safe address because we cannot call this function on any random address. We have to call it on a variable which exists in memory, okay? So you see here that we no longer have this. We had an ampersand when we used pointers because you had to give the address of something, but we no longer have the ampersand here. This function knows that I'm getting a reference, and so C++ takes care of it for you. So this is one of the benefits of using references, is you no longer have to mess around with a bunch of crazy syntax. So if we set a equal to 10, this is looking up the address and changing what lives at a to 10, not some copy of a. So if we print out I here, we will get 10 instead of 12. Okay, so here is passed by value. If we stick a little ampersand in front of here, then we've changed it to pass by reference. So we're going to use references wherever we want to be able to change something. All right, and the reference will always, quote unquote, always be valid. 99.9% of the time, or like a lot more than that actually, it will be valid unless you're doing something crazy. Here's another example where you want to use pass by reference. Let's say we don't necessarily want to modify the thing, but we've got some large amount of data, okay? So if we have some class called big data, for example here, and we have a function that does some machine learning for us, okay? So I kind of gave this example before, and we want to pass our large amount of data, our large class, into that function to do some machine learning or something, right? Do some stats, do some visualization. If I do this, then the big data object is copied, and that can be insanely slow, okay? So we're passing a copy of the big data object into the machine learning function. We don't want to do that. What we want to do is the following. So in order to not copy the big data, we're going to pass in a reference to the big data. Okay, so that's just, it's a very small, it's basically just an address. So we're only passing an address in. But now we've also said, and we touched on this as well for the last lecture, that if I pass in a reference to something, it can be modified. And that's something that sometimes we don't want to do. Okay, so in order to say, okay, this is a reference, but you can't modify this, right? I'm going to say const. So what this is doing is it's passing in a const reference to a big data class, and the variable name is D. Okay, so again, a reference is just a memory address, which on a 64-bit machine is 8 bytes. Okay, so rather than passing in like our 20 gigabytes of machine learning data, we're just passing in 8 bytes. And since we don't want the data to change, we're making it const. All right, so passing by const reference. Whenever we want to pass a variable to a function that we don't want to be modified, use a const reference. Okay, so that's a general rule. However, there is an exception to it. Whenever we pass a reference to whenever we pass any variable to any function, and we don't want that variable to be modified, use a const reference. Gets a little bit tedious, but it's good practice. However, and the reason for that is that const declares that the variable cannot be modified inside the called function. And all we're doing is we're copying the memory address, or the reference, which is an 8-byte reference, which may be far less data than the data that we're passing into the function. So your code should have a lot of things that look like this, where we're passing in const big data, whatever, const my class reference, whatever. There are exceptions to this, okay? Pass primitives by value, okay? So we don't want to pass primitives like integers, floats, chars, stuff like that. We don't pass those by reference. The reason for that is we really only want to pass const references when the data type is larger than an integer, right? Because what this says is instead of just copying the value of an integer over, you're copying a reference that then needs to be dereferenced. And it turns out that this line in practice is faster than this line. So you could do either of those, okay? And up until about 10 years ago, when I realized how slow this could be, I was using this one line. You can pass, you totally can pass const references to primitive data types, but you generally don't want to because it's a little bit slower, okay? So there's nothing wrong with it. It's just slower. And the second part, and we're not talking about this yet, okay? We'll get used to this in the future of this course. But you do want to pass smart pointers by value rather than by reference, okay? You can pass them by reference. It's fine most of the time, but you do want to pass them by value so that their constructor and destructor can take care of the internals. And we'll talk about that a bit later. Okay, so let's get into the part of C++ that will completely change the way you code in C++ and completely change your opinion of it as a language and how easy and safe it is to use. And that is RAII, which is a horrible name. I don't know who came up with it, but it stands for Resource Acquisition is Initialization. Oh my God, what in the hell is that? So RAII is the concept of binding the life cycle of a resource that must be acquired before use to the lifetime of an object. That's the strict definition. What does that mean? It's going to make life easier for us in a way that automatically manages memory and resources and encapsulates that within an object. So the object is going to do the memory management for us. And then whenever we use that object, we don't have to worry about memory management. So let's have a look at that. So the way we're going to implement RAII is that we are going to encapsulate our resource into a class. So we're going to come up with like a class that wraps around our data. Someone said they should come up with better names. So yeah, this is not like an official, like this isn't in C++. There's no RAII class, but it's just like, 70 years ago when programming started, they came up with this. All right. So we're going to encapsulate every resource inside a class. The class constructor is going to acquire the resource and initialize it. And then the destructor is going to release the resource. Okay? So the constructor is going to get the memory. The destructor is going to free the memory. The class itself should be instantiated such that it either has automatic storage duration or it's inside another RAII object. So we can kind of chain RAII objects together in order to keep it safe. So let's look at an example of what I mean by this. Let's say that I want to make a class called intArray. Okay, and I'm going to do this in the live coding session, but I just want to give you like sort of a heads up of what we're doing. Instead of just in my code, like we saw before, if I want an int array, I'm going to say int star array equals new int whatever. Instead of doing that in my code and then later having to free it and worry about that or worry about a memory leak, I'm going to wrap my int array inside its own class. And here's how it'll work. I'm going to have a private variable, which is the pointer itself. Inside my constructor, so my constructor for the int array is going to take in the size, and I'm going to say array equals new int size. So the constructor is acquiring the resource. It's asking for the memory from the heap. So the constructor acquires the resource. The destructor releases the resource. Okay? So the destructor is going to delete the array. And when you want to free an array in C++, that's the way we do it. And if we want to get access to our data, we're going to overload the operator. I'll get into that in the live coding session, but this is how we can get access to our data. All right, let's look at what our code looks like now that we have this thing called int array. So if I say int array array 10, then I've allocated an int array of size 10. I don't see any pointers here, right? I don't care how the memory was gotten for this int array because it's all done inside the class for me, okay? Now, I'm going to do something with the array. Let's say I get some values, I set some values, blah, blah, blah. And then I get down into, I leave the scope. And remember what happens? When we leave the scope, every variable that was stack allocated on that in that scope is going to be deallocated. So when a class gets deallocated, its destructor is called. So we've allocated this int array class on the stack, okay? When that was allocated, it got some heap memory. Now, down here, when this scope finishes, it's going to call the destructor of this class. Inside the destructor of that class, it's going to free the memory properly. See how that works? So no, C++ is not a garbage collected language. But we can we can't make it garbage collected, but we can make our data structures and our classes in a way so that we, in practice, never have to worry about that. The only place we ever have to worry about it is we have to make sure that our class is written properly. But once our class is written properly, we're good to go, right? And we can just use it like this, and we never have to worry about memory. And it turns out to be faster than Java garbage collection because it's deleted exactly when we want it to be deleted, rather than having some garbage collector having to come get it. Okay, so what we did here in this example was we said, okay, I'm going to want to have an int array. So in order to do RAII and manage my memory, I'm going to have a class that wraps around that, okay? Now, it's going to be really annoying if for every possible data structure that we can come up with, if we ever want to put it on the heap or be dynamically allocated, we're going to have to make our own class. Right? We don't want to have to be doing that. So luckily, C++ has done that for us. Okay? So, smart pointers. What is a smart pointer? It can be very cumbersome, as I just said, to create our own RAII classes for every single data type that we want to store a pointer to. Luckily, C++ contains some different smart pointers. I am not going down the rabbit hole of explaining what all the different smart pointers do, when you want to use pointer A, when you want to use pointer B. For this course, it's going to be good enough. We're going to use standard shared pointer, okay? And what standard shared pointer does is essentially what we did here, okay? When you create a shared pointer to a type, it's allocating it. When that shared pointer goes out of scope, it deletes it. Done. Now, a shared pointer has an extra step where if you pass it around through different functions and stuff, it actually has an internal counter that says, like, there are currently 3 functions using me. So whenever I go out of scope, I'm going to decrement that. And whenever I go out of scope for the final time, I'm going to free it. So there's a little bit of extra stuff behind the hood. But again, this is not a C++ course. This is a game programming course. So we're just going to use shared pointer because it just works and it's great. And for anyone out there saying, oh my God, he's using shared pointers in a game programming course, it's going to be so slow, dude. I know. I told you at the beginning of this course that this is a compromise between the utmost speed and usability. And at the end of the class, I will show you how, if you actually want to go write a AAA game engine, how to get rid of the shared pointers. Okay? But for the most part, they're going to be fine. And they're going to enable us to do lots of stuff very easily. And a lot of the time, perfect is the enemy of good enough. And so shared pointer is good enough for what we need. And what it does is it handles the RAII for a given type. Alrighty. So a shared pointer, what does it actually do? It is called a reference counted pointer, meaning that it keeps track of how many things are using it. Someone asked a question. Smart pointers are internally raw pointers wrapped inside a class. Exactly. Okay. So just like here in this example, we had a pointer wrapped inside a class. It just happened to be an array, right? A smart pointer is essentially the same thing. It's a pointer wrapped in a class. However, it's also templated, so it uses generics, so that we can have a shared pointer to whatever type that we want. So we can have a shared pointer to an int, we can have a shared pointer to a float, we can have a shared pointer to a big data, doesn't matter. So it's a reference counted pointer. Internally, what it does is it has an internal counter. The internal counter is set to 1 in the constructor. Every time we copy the shared pointer, its counter increases by 1. Every time it's destructed, its counter decreases by 1. And when the count reaches 0, the resource is deallocated. Okay? So I'm going to leave this. Why not? Okay. So what we can do here is we set up a shared pointer. So instead of saying the syntax for shared pointers is a little bit different. Okay, so instead of saying my class star p equals new my class, we're going to say standard shared pointer my class p, and then in the constructor we're going to pass a new my class. Now this is the old syntax. We're not going to be doing it this way in the course, but I just wanted to show you in case you go Google online and you find this. Okay, this is a syntax that can be used. So yeah, it's a little bit confusing, I know, but trust me, when we get to the game, it's going to be dead simple, okay? So the syntax that we're going to be using in this class is auto p equals standard make shared my class with some arguments. So instead of my class star p equals new my class, we're going to be doing it this way. And trust me, I know that this syntax is a little bit confusing right now, but it's like riding a bike, right? Riding a bike, you could go read 10 books on how to ride a bike, and then you get on a bike and you're still going to fall off, okay? But we're not going to be doing a lot of book reading in this course. We're going to be doing a lot of getting on the bike and falling off, okay? And you are going to use this, and it's going to be a little bit confusing at first, but then you're going to be like, oh, okay, I see how it works now. Or at the very least, you don't see how it works, but you're going to be able to do it, okay? So again, this is a compromise course where you may not completely understand exactly how a shared pointer works, but it's going to enable you to do a lot of cool stuff. So we're going to use it. All right. I just have this slide in here on inheritance in C++. So just like Java, you can have a base class and a derived class. And the syntax is just a little bit different. You can have public inheritance and private inheritance and all sorts of stuff like that. 99% of the time, we're just going to say, okay, my class, public base. And that just means that it inherits from a base class. I just have that in there as a reference for you. We're not going to get too much into inheritance because it's essentially the same thing as Java. Okay. So all of that meaning, how are we going to allocate data and pass data in this course for our game engine? First, if possible, we are going to use the stack, okay? Small local variables get like integers, floats, doubles, they get stack allocated. We are going to pass these, if they are very small, just copy construct them, so just pass ints into functions. But if the variable is big, so greater than 8 bytes, we are going to pass by a const reference. If you need heap memory, do not use a raw pointer. We are not using raw pointers in this course. Nowhere in this course will you see int star a equals new int. Everywhere that we need to use a pointer in this course, we are using a shared pointer. Okay, so we're using smart pointers. We are using the particular one called shared pointer. And we'd say, okay, standard shared pointer base equals standard make shared derived, or standard shared pointer t my big data. Okay, only when absolutely necessary do we use raw pointers or new. Okay, someone said, should we pass strings by reference? Yes. So a string is going to typically contain a fair amount of data, much more than an integer. And so whenever we pass a string into a function, we want to pass that string by a const reference. Now again, I know that I gave you a lot of information, okay? And that is almost impossible to dissect in one sitting and just have it absorb, right? Like it's me telling you, okay, in order to ride a bike, hop on the bike while it's moving a little bit, make sure you're absolutely perfectly balancing your weight on the left and right. And then when you move, you kind of have to lean forward and like steer the thing, but also lean to the side and then just throw you on a bike and hope that you can ride the first time. Okay. That's not, you have to practice, and we're going to practice a lot in this course. Someone had another question. String is internally a raw character pointer. Exactly. So string, standard string, is doing RAII for us. It is allocating the string data, and when the string goes out of scope, it is deallocated, and then its destructor is called, and it frees that resource for us. So standard string does the RAII around a raw character pointer. It's a good question. The last thing I want to talk about before I get into the live coding is C++ templates. And I know so again, the official lecture here goes until the slides. And then because I want to give you as much information as possible, I'm doing extra work here to give you some more live coding if you want to follow along. So C++ templates are extremely powerful. They're easy to use, but they can be very complicated. C++ templates can be one of the most frustrating things that you ever work with if you run into errors, but we are going to keep it very, very simple in this course, okay? And in the live coding, I'm going to give you an example of why we want to use templates. They can be used to implement generics, meaning that if I want to have a vector that stores anything, then I can do it with a template. And we'll show that in the live coding. So let's just do a coding example. All right. So that's the end of the official lecture. And now I'm going to get into some live coding so that I can show you some cool stuff. Alrighty. So let me pull up my notes and we're going to start doing some live coding. So again, if you're a student in the course and you have another class now, if you're watching live, by all means, you don't have to watch this now, but come back to this. It will be here if you want some more practice with coding C++. Alrighty. So let's open up some code. I've already got my, my template code here typed up. So again, we're including IOStream so I can print some stuff out. I've got my int main and I've got my return 0, and that's it. So let's do a little bit of practice with all of the stuff that we said. And someone said, can you please show us variables stored on stack are contiguous? Yes, I will. Okay, so let's do that. So first, let me make a variable. So int a equals 10, int b equals 25. So these are stack allocated variables. All right. So what I'm going to do is I'm going to print out a, and then a new line. And then I'm going to, oops, I don't have my semicolon. Standard cout b, and then a new line. Okay, so I'm going to compile and run that. I'm going to hopefully get 10 and 25, and I do. All right. So now what I can do is I'm going to say, let's look at the address of both of these things. So I can print out the address of A, and then a blank, and then the value of A. And I can print out the value of B, or the address of B, and then the value of B. So again, if I use ampersand, that is the address of a variable. That tells us literally the address in RAM where that thing is stored. Okay, so let's look at this. Now, I've got a huge hex number here. That is the address where the variable A is stored. That's it right there. And the value of that is 10. Here, I've got the address where B is stored, right? This is a 64-bit integer because my computer is 64-bit, okay? And it has the value of 25. And if we look here, this address ends in 60, and the very next integer that we allocated is at 64. Since an integer is 4 bytes, well, let me do this too. So what we can do here is I can also print out size of A and size of B. Size of is a function built into C++ that tells us how many bytes does this data structure need in order to be stored. So let's compile that again. Oops, I didn't put a blank in there. Okay, so let's do that. All right, so here, and you can see when I ran it again, it had a different, this is a different memory address, right? Because I ran the program a different time, not guaranteed to be in the same place in memory. But A has the value of 10, it takes 4 bytes, and it lives at this address. B has the value 25, it takes 4 bytes, and it lives at this address. And this address is 20, this address is 24, which is 4 later. So it means that in memory, A is right next to B, exactly how I said it would be in the thing. All right, let's write a function now that does this, because I'm going to probably want to do this a number of times with some different data, but I don't want to have to type that for each time. So let's write a function. So let's say I'm going to write a function. That function is going to be void, right? Because it's just going to print something. I'm going to call that pp for pointer print. I am going to pass in a reference to a variable. Okay. Then I'm essentially going to do this. So let's just copy and paste this up here. Okay. Remove that line, remove that line. And now what I can do is I can say pp A and I can say pp B. And that should work. Okay, so I get the exact same thing. Now I have that function that does that for me. Okay. Someone said, shouldn't we pass primitives by value? Yes. However, in this, that is a very good question, and I'm very glad that someone asked that. However, what I'm trying to show you here is the address of this variable, of that A, and the address of this B. If I instead had passed, well, let's just do it and see what happens. If I just pass A into here, A gets copied here. Actually, let me change this to I to make it a different variable name. So we have I, and I. Okay. So if I pass A into here, it will be copied. And then the address of the copy is what will be displayed. Do you get that? The address of the copy gets displayed. So if I run this now, look, I get the same address for both variables because they're both copied into that function. All right. So yes, this is a different variable. This is not the original A. And because this is the variable that lives at this stack frame whenever we call pp, it's actually going to have the same address. So we want to pass a pointer into it, or a reference into it, or a pointer, so that we actually get the memory address. Okay? All right. So let's look at an array now. All right. So let's say we have int array, and it could be called anything, 10. Okie doke. So int array 10. That's how I do a stack allocated array. Now, let's say that I want to print all of those things. So I'm going to say for size t, I equals 0. We talked about that last time. I less than 10, I plus plus. And now I'm going to call my pointer printer on array I. So what does this do? Oh, wow. Okay. What in the hell is going on here? This is weird. All right. Let's look at the values. 0, 0, negative 119 million, 21,989. 0. What is going on with these values? Well, we didn't give them a value. Remember how I said that in C and C++, it doesn't waste any time. It's so fast, it doesn't even give these values, right? It just says, hey, whatever happens to be in memory at your memory addresses, that's what we're putting here. So in C++, there's a nice shortcut. If you want to give these all default values, which for an int would be a 0, I can just give it this syntax. Okay, so let's do that again. All right, now they all have values of 0. Let's look at their addresses. So since this is a stack allocated array, it's going to be contiguous in memory, right? So each of these should be 4 bytes away from each other, and they are. C0 plus 4 is C4 plus 4, C8 plus 4, CC plus 4, D0. So we can prove that this is contiguously allocated in memory. Got it? Now, let's do another thing. Let's make a heap array. I'm calling that heap array, and that's got to be a pointer, right? And that's going to be equals new int 10. So I'm going to do the same thing, but I'm going to do that to the heap array. And now I'm going to do the same thing, but let me do it for the heap array. Heap array. All right, perfect. So this up here, this is the stack allocated heap, or the stack allocated array. Down here, printed right after, is the heap allocated array. So you can see here that the address of stuff on the stack is very different than the address of stuff on the heap. Okay, so this starts with like 563. So in my computer, this memory is actually living several gigabytes away from this memory, which is kind of funny, but that's how it is. All right, so this memory, that's the heap allocated memory, and it has a different address than the stack allocated memory because heap and stack are actually quite different. They're quite far apart in memory. All right, so this would actually now be, I did not free that memory, so that was a memory leak. But we're going to get away from doing that anyway, so don't worry. All right, so let's look at pass by reference versus pass by value, like we did before. So those are addresses. Oh, let me do something else here. No, I don't want to do that. Okay. Undo. There we go. All right. Phew. Let's do a little bit more about pointers. Okay. So I'm going to have my int a equals 10. Then I'm going to have int star, which is an integer pointer. Some people put it like this. That's fine. So an integer pointer, that is going to be a pointer to a, and this is going to be equal to the address of a. Okay. Now I'm going to have int b equals 25, and I'm going to have an int pointer to b equals the address of b. So what I do is if I call pp on a and pp on b, I'm going to have the same thing that I had before, right? Looks kind of the same. Now, let me try calling pp on pa. What's going to happen? Oh, it's going to say, I can't do that because here, this is expecting a reference to I, okay? A reference to I, but we're passing in a pointer to an int, not a reference to an int. So that's a mistake. Okay, so now what happens if I say whatever lives at PA, I'm going to change that equal to 17. Now, oops, let me do that first. Now what's going to happen? Well, instead of 10 here, we have 17, right? Because I say whatever happens to be at the pointer, or sorry, at the address that this pointer is pointing to, which it's pointing to A, I'm going to change it to 17. Similarly, what I could have said was whatever, so I'm going to dereference this memory address or this pointer, and whatever happens to live at A, right? Whatever happens to live at A, I'm going to dereference it and make it 17, and that's the exact same thing. So where I had just said star PA equals 17, these two lines are exactly equivalent because up here I had set PA equal to ampersand A, which is the address of A. Okay? So, here we go. Now, this is where stuff starts to get interesting. Okay? This is, if you were taking a security course, this is where you would start doing security stuff. We're not going to do this in this course. I just wanted to show you something, why pointers are dangerous. Look at this. So we showed that the variable A lives in memory 4 bytes before the variable B. Okay? Or 1 integer away, essentially. So watch this. I'm going to modify A without ever accessing A or its pointer. So if I wanted to modify B, I could do this, right? So B equals to 17. Oops. Oh, PB, sorry. So this is me modifying what lives at PB, which is the variable B. So now we'll print out 10. Ah, geez. 1 second. Oh yeah, I modified it. Sorry. I modified it before, after it printed. So star PB equals 17. That will modify what is at B. All right. So there we go. So I apologize. This is live. We're going to have a few little mistakes. So now instead of 25, we get 17. Now, just watch. Pointer arithmetic, if I say PB minus 1, what that does is it knows that PB is an integer, okay? So because it's an integer, if I subtract 1 from it, it's going to subtract the number of bytes that's in A, or sorry, that an integer takes. So since an integer is 4 bytes, this is actually going to be the memory address of B minus 4 bytes. Since A lives at the memory address of B minus 4 bytes, now A gets modified. See that? Isn't that crazy? We've modified the value of A without ever actually explicitly saying so. And so if you modify pointers, you're going to get a whole bunch of stuff that goes crazy. All right? And this is why raw pointers are dangerous. And this is why in this course, this right here is the last time, well, not the last time, but one of the last times you'll ever see a raw pointer. All right. Okay. So what we're going to do now is let's demonstrate. Let's see. What am I going to do? Let's demonstrate RAII by making our own int array class. Okay? So we're going to make a class called int array, and we're going to do what we did in the slides. So this int array is going to encapsulate an array, and I'm going to give that the m_Hungarian notation because it's a private member variable. Then public to int array, I want to have int array be a, we're going to take in a size. So this is going to be the size of the array, right? Then I'm going to have a, so let's do that. How do I allocate this? Well, I'm going to say m array equals new int size, right? So if I wanted to make a dynamically sized int array out in the wild, I would have to call this new syntax. But right now we are demonstrating RAII by wrapping this inside a class, okay? Now, the other thing about C++ is that it does not know the size of its arrays because all this is a pointer. It points to the first element of the array, but it doesn't know how far that array goes. So I'm going to have to store that size as well. And that is the size of the array here. All right, so that's the size of the array, and I've got the pointer to the data. So here, as I said before, I talked about initializer lists, so I can say mSize and put size here. And similarly, how I did this line down here, I could even do something like this, where I say mArray and then go new int size. So I can actually do that in the initializer list like this. So let's just leave it. Now let's compile, see if anything complains. Expected qualifier, Oh, I'm not supposed to have this right here. There we go. So now we compile. M size will be initialized as okay. So it's complaining that I declared this variable second, but I'm initializing it first. And some compilers actually complain about that. So let's just put it above, and now we'll recompile, and okay, now we're good. So we're on our way. We have that the constructor acquires the resource. Okay, the constructor acquires the resource. And I'm going to call here, I'm going to say standard cout array constructor. All right, so now we're going to print out whenever we construct the array. Now, how are we going to add things to the array? Right? So let's not do add, but let's just like get and set. So if I want to get something from the array, then I'm going to say int get. I'm going to have an index. And getting from the array will not change the array. So this is going to be const. Remember our const correctness talk. And now we're going to return array index. Perfect. So that's how I would get something from this array. Now I want to be able to set something in the array. So I'm going to say void set. In order to set something, I'm going to need an index and an int value, right? This is not const because I am going to be changing things. And what I'm going to do here is I'm going to set the index of that array equal to value. Okay, so now I've got a fully functional dynamic array. I can get things from it, I can set things from it, or set things to it. So down here, let me call int array, and this is going to be called my array, and I'm going to set this up with 10 elements. Okay, now what I'm going to do is I'm going to call my array. Oh, before I do this, let me actually write a function that prints this out. So I'm going to make a function called print. That's going to be const. And then I'm going to say for size t I equals 0, I is less than m size, because that's the size of the array, I++. For all of you C++ nerds out there who say, you know, you should put ++i here, that is optimized out by the compiler. So by saying that, you're admitting that you think that matters. So I++ is fine here, some ++i. Anyway, so we're going to say standard cout. We're going to print out the index followed by a blank followed by the value, which is mArray I, followed by a new line. Okay, so if I come down here now, and if I just initialize an array, and then I call my array.print, what happens? Okay, so this is all initialized to zeros. Now it turns out that when you say int star whatever equals new int, the new operator in C++ will set it all to zeros for you. Okay, just lost my window. Okie doke. So now let's actually do something to the array. So I'm going to say my array dot set. So I'm going to set in index 4, I'm going to set the value of 7. And in my array dot set, index 2 is going to get the value of 134. And then when I print, look at that. So index 4 has the value of 7. Index 2 has the value of 134. We have, who can tell me what I'm missing? I'm allocating the array, but I am not yet destructing or freeing the array properly. Okay, so the destructor is something that I have to write, and the destructor uses this syntax. It's the same as the constructor, but it has a tilde in front of it. And what I have to do here is I have to call delete and then this. Just a weird syntax, but it says delete whatever's at M array, and it is an actual array. Okay, so that is going to free the memory that I allocated. All right, but down here, look, and in the destructor, I want to do one more thing, which is standard cout array destructor /n, boom, boom. All right, so now if I do this, it calls array constructor because the array was initialized. Then I do some stuff with the array, and then at the very end of the function, the destructor is called and it cleans up everything for us. So look at that. We wrote our own function, or we wrote our own RAII class that wraps around this array. Someone is asking out there, how can I grow the size of the array? You can delete it and reallocate it, or you can call realloc. That's not the point of this lecture, so I'm not going to spend time reallocating or growing things. It's really not the point of this lecture. So I'm not going to answer that. Please just go Google it. So it'll just take too much time. So I apologize that I can't answer your question right now. What was I going to say? So I have this now. I've created this class. But what if I don't want ints stored in here? What if I want to store floats or any other class? Well, what am I going to have to do? I'm going to have to write a float array. I'm going to have to write a my class array, right? So turns out that just like in Java, we have something called generics. And generics allow me to write one piece of code that does a bunch of different things for us. And so in C++, the way we implement that is called a template. And the way we do it is the following syntax. Template class T. You can also say template type name T. Okay, so you could say type name here instead of class. So let's just leave it as that. Doesn't matter which one you use. And then in here, wherever I said int, I'm just going to replace with T. And you'll see how this works. So up here, this is no longer an array, than int array. This is like a dynamic array. Okay, so it's no longer just going to store ints. Down here, wherever I had int, I'm going to now store T. So this class is written to be usable by any type, and that type is just represented by this T. Okay, so if I come down here, this is going to change to a T. Down here, when I return something, that is going to change to a T get, right? Down here, when I set a value, this is going to be a T value. And when I print, this is okay. So now what I have to do is it's no longer called an int array. It's called a dynamic array. And this dynamic array now needs to take a template argument to tell it what type I want it to be. Okay, so this is going to be a dynamic array of ints. Hopefully I didn't make any errors. Oh my God, I did make errors. All right, so where did I make my errors? Thank you, templates. All right, so let's see. I've got some, oh, I know. I didn't change the name of my constructor or destructor. So constructor and destructor have to be the same name as the class. And I left those as int array. Let's see if this works. All right, perfect. Now I have my array, I have all the same stuff, but I could do it with floats as well. So let me just show you an example here. So if I set this value to like 7.14 and this 134.420, right? So these are float values that are going to be stored as ints. So when I go to print those values, it's actually printing out the integer concatenation of those things, right? So it's a float to int conversion. So if I actually do want to store floats, then what I can do here is just change this to float, and now I'm storing floats so that when I go to print it, the actual float values are there. Okay, see how that works? So this is RAII. You can see down here, I've got a dynamic array, I'm setting values, I'm getting values, and I don't need to worry about memory. There's no worry about memory in this code. And we are going to do this for everything in our game, so we never need to worry about memory. One other thing that I wanted to show you is that if this is a dynamic array, right? Well, saying like get and set, that's such a Java way of doing things. This is an array. I want to be able to say like my array 3 equals 20, right? If it's array, I want to be able to say that. And the cool thing about C++ is we can do that. And I'll show you how. So here we have something called operator overloading. So operator overloading, what in the hell is that? I can create a number of different operators on this class that I can use in any way that I want. And the cool thing is, one of those operators is the square bracket operator. So I can say operator square bracket and then give it an argument, which is the thing that goes inside the square bracket, and this is going to be an index. And so I'm going to want to call the square bracket operator via index, okay? So that's what I'm going to do. What is the type of this? Well, I'm going to return a reference to a T. And the reason I'm returning a reference to a T, I'm going to show you in a second. But all I have to do in here is return marray index. Okay? So marray index is going to be returned. So down here, instead of setting things, I can do the following. Now I've got a float array here. So I'm going to say my array 3 equals 3.14159. And my array 2 equals 2.78. Okay? Now, what happens when I actually call this? So this here is going to call the bracket operator of my class, which takes in an index, and it's going to return marray index. Up here, it's returning a reference to that memory, right? So this is a reference to what lives at the third index of the array. So what will happen is that will actually change what's in the array. Okay, you see how that works? But if I had just said this, T operator, then what gets returned is a copy, okay? And it actually doesn't let me do it because I'm trying to set a copy of something. But essentially, this would, that would be setting a copy of something. It wouldn't actually change the array. So here is what we do, and now we are able to use this just like a normal array without having to call .get and .set. Isn't that convenient? It's pretty cool. Now, it turns out, what if I had something like this? All right. What if I had a const dynamic array? Well, I'm going to print that out. That's fine. The const dynamic array means that this array should never be modified. Okay? But let's say that I want to just print, I want to print my array 2. So if this is const and I just want to print something, well, that's fine, right? I'm not modifying it. I just want to do that. So, all right. Just for, I'm not trying to be rude whatsoever. And I'm very appreciative that people are following along in the chat. But every time I say something, you don't need to like tell me what I'm about to do. I'm trying to monitor the chat in real time for questions. So if you just keep typing, like it's a little bit distracting if you're just saying what I'm about to do. So try and just leave it. I appreciate the following along. It's amazing. It's nice to see someone awake out there. But I'm trying to monitor for like questions. So if you have a question, that's great. But if I say something like, well, how will I do this? The spoiler is that I know how to do it, right? So I'll specifically ask the chat when I want to type stuff. But you're absolutely right, is that, let me just show you what happens. This again is running into something called const correctness, okay? So what's happening here? Why did it give me an error? Well, it's because I am calling this operator on the my array, okay? See this? If this is const, then this function also has to be const. So up here, I have to say that this function is const. Now, let me run it again. Now it works, okay? So, yeah, and I could put a const in front of this as well, and that would allow me to print those out. Oops, with no type. Oops, const t. So what this does is it allows me to get access to see the values of this array in a const way, and I know that I'm going to be returning a const reference to that thing as well. So let's do this, and now I print out that 0. But watch now. If I try to use that function to modify the array, my array 2 equals 17, right? And let's say, okay, now we don't have a const array anymore. I know this is going a little bit into the weeds, but I'm just showing you more const correctness. So down here, if I have an array and I want to modify it, well, I can no longer use this function, okay? The reason I can't use that function is because it's returning a const reference. So this is saying that the reference that it's returning is const. I can let you see the data, but I don't want you to change the data. And so what you have to do is, if you want to be able to both change the data and see const data, is you sort of had to have two versions of this function, okay? So t star operator here, size t index, and then I can say return m array index. So the cool thing about this is that if I do something like this, standard cout my array 2. So what's happening here? I know this was a whole lot to take in, but we'll go over it again. I have my class, which I've declared here. It's an array of size 10. I'm going to be setting something in the array using the square bracket operator. And then I'm going to be getting access to the data as well using the square bracket operator. And C++ allows me to have both of these functions so that whenever it sees that I'm trying to set data, it's going to use the non-const version. And whenever it sees that I'm trying to get data, it's going to use the const version. And it turns out that using const functions allows the compiler to do some nice little optimizations. And so whenever you do something like you have your own data structure and you want to write the operator overloading, make sure you have the const and the non-const versions of the operator overloading. And then we run it and it works perfectly. Okay, so in that amount of time, we've gone over pointers. You know what pointers are. You know what pass by reference and pass by value is. You know what RAII is. You know how memory works now in C++. You know what templates are in C++. You've created your own templated class. And you know about operator overloading in C++ as well. And so this is almost all of the knowledge that we will need to go forward in this course and create some badass games. We are going to create our own whole 2D game engine from this, and it's going to be really fun.